Okay. It works now.
So which computer is your primary computer? That one?
Well, right now my primary computer is at Dell because it broke, and so this is the loaner. And then I have this was being flaky for my personal laptop. And then when I came here, they're like, "Oh, we have a loaner laptop for." So right now I have like 3 or 4 laptops. So, yeah, right.
It's an Intel laptop, the Dell one?
This is NCAR, yeah.
You go
The one that's
to
gonna-
start
It's also NCAR, yeah.
and introduce yourself.
Oh, thank you. No thanks. No thanks.
It's at the main seminar room.
All right.
Can everybody online hear us? Yeah, okay. Good. Alrighty, welcome to the AMWG not joined with anybody meeting, just the AMWG. Yeah, I'll let Jan take the mic.
Okay. Thank you so much, Peter. Can everyone hear me fine? Okay. I will just start. Good morning, everyone. Today I'm going to present something that might be slightly different from other talks because I'm going to present a mechanistic study that looks at the relationship between vertical wind shear and convection development. So why do we care about vertical wind shear? Because we know it's important for organizing convection from mesoscale convective systems to Madden-Julian oscillation, which is critical in the large-scale circulation pattern. Most existing literatures about this topic are mostly focused on either like a single score line system or really idealized warm bubble experiments. And if we do want to include this important impacts of vertical wind shear on convection development in the large-scale circulation model, such as CAM, we do want to have a more robust statistical relationship between the two, which is not being done in the previous studies. This actually motivates us to propose an ensemble approach to get the convective responses to vertical wind shear in a less storm-like and more realistic environment. And we want to inform a more physically based convection wind shear relationship to be used in CAM. So this is our overarching goal. Some specific questions we're going to understand today is, first, do the convective characteristics respond to vertical wind shear monotonically or non-monotonically, and why? The second is, what drives the differences in the surface precipitation response with different wind shear magnitudes? And the third is, does organization occur under a certain or particular wind shear magnitude? To answer those questions, we first need to simulate a cloud field. And we did so by running a cloud resolving model. We first run this cloud resolving model to a radiated convective equilibrium state, which has no large scale forcing. We use a horizontal resolution of 500 meter, which is kind of fine, and a stretching vertical coordinate with temporal resolution of 10 seconds. As I mentioned earlier, because we want to get an ensemble response to the vertical wind shear, therefore we created 20 ensemble members with initial conditions that were generated by the output from the equilibrium run. And each ensemble member is separated by 12 hours. And then we run each ensemble member for an additional 3 hours, subject to each different vertical wind shear profile. And this is the basic RCE state that we get. We can see that the surface precipitation and also the surface fluxes, they reach to an equilibrium state at about day 20. So in later talk, all my analysis results will be ensemble averages of 20 ensemble members. Okay, so this is then in terms of the vertical wind shear profiles we added to the convective system. We actually tried a series of different wind shear profiles, such as U-shape, linear shape, sinusoidal shape, and different kinds of wind shear profiles that you can imagine. But we figured out that the linear vertical wind shear is actually the wind shear profile that introduces the most convective response. Therefore, in this work, we are using the linear vertical wind shear throughout. So the panel, this left figure shows the all the different vertical wind shear profiles. Ranging from L1 to L9, the vertical wind shear increases with the increment of 2.5 times 10 to the fourth per second. We also include a control simulation that has a background wind of -5 meter per second, which is typical of a tropical atmosphere. And the response of the convection to the imposed vertical wind shear profiles is shown to the right panel here. In terms of surface precipitation, sensible heat flux, and latent heat flux. And this bottom panel is actually the ensemble spread, as I mentioned earlier, because I used 20 ensemble members for those results. So the bottom panel is actually the ensemble spread. If we look at the surface precipitation, we can see that initially the surface precipitation decreases in the first half an hour, and then starting from hour 1 into the simulation, it increases rapidly until it reaches a peak value at about 1.5 to 2 hour. So one interesting finding that we have is that we actually observe like a minimum surface precipitation response at L6 case. So this black curve, I don't know if you can actually see that. So this L6 case, if we look at the vertical wind shear profile, is actually a moderate vertical wind shear that is neither the minimum nor the maximum wind shear. And if we look at the surface sensible and latent heat flux, we can also observe a very similar pattern in which the sensible and latent heat flux is minimum at L6 case. That is at a moderate vertical wind shear case. So based on this result, we actually can see that there is like a non-monotonic behavior of the convective response to the imposed vertical wind shear. In addition to the domain mean surface precipitation, we also plot the mean, minimum, and maximum precipitation over time. And remember that like this 1.5 times 10 to the third is actually a linear 6 case. So what we see is that like when the wind shear magnitude is lower than this value, the mean precipitation and also the minimum precipitation decreases as a function of increasing vertical shear. Whereas once it exceeds this value, the precipitation response actually increases rapidly afterwards. And consistent pattern is observed for the convective heating and moistening as well. So if we look at this cumulus heating curve, after L6, the peak cumulus heating, it shifts down from 6 kilometer to 4 kilometer. And between 2 to 4 kilometer, the apparent moisture sink becomes more positive after L6 case. And between 3 kilometer to 8 kilometer, the eddy moist kinetic and static energy also increases. So this all indicates that like once we impose different vertical wind shear onto this convective system, the surface precipitation response and also the related convective heating and moistening response exhibits a non-monotonic behavior instead of a monotonic increasing or decreasing behavior. And why so? Because we think the surface precipitation is closely tied to the total condensed water budget. So next, we're going to analyze this total condensed water budget in more details. So we can write the total condensed water budget as a linear combination of condensation rate, evaporation rate, and surface precipitation. This bracket denotes the vertically integrated value from the surface to the top. We can also write precipitation efficiency and evaporation efficiency in terms of the surface precipitation rate and total condensation rate. So the reason we also care about the evaporation rate is because based on some earlier studies, they suggest that the entrainment and detrainment process between clouds and environment is very important in determining the relationship between vertical wind shear and convective organization. So we want to look at like how important this term is represented by the evaporative efficiency. And this is the figure, the condensation rate and precipitation efficiency that we got. So one thing we can get from this condensation rate is that the general pattern, the varying temporal trends of condensation rate is very consistent with the temporal trend of surface precipitation. Additionally, we also calculate the spread of the condensation rate among all the different shear cases, and it is very quantitatively close to that of the spread in surface precipitation as well. On the other hand, if we look at the precipitation efficiency, where you can think of it as evaporation efficiency, the pattern is actually less consistent with that of the surface precipitation. Where so when we calculate the spread among the different shear cases, it's much less compared to both the spread in condensation rate and surface precipitation. So just based on this calculation, we thought the condensation rate instead of the evaporation is the primary driver of the change in surface precipitation. And so if we look at this, condensation rate even further, as it is directly related to the cloudy updraft mass flux, what we plotted here is the mass flux as a function of time and height. So going from control to the L6 case, we observe like a minimum in the mass flux distribution in L6 case, which is consistent with the minimum in surface precipitation and Warsaw condensation rate. And we know that we can also decompose the mass flux further into updraft cloud fraction and vertical velocity. So the general trend in cloud fraction is that once we increase the vertical wind shear, the fraction actually increases in the low to mid troposphere as the vertical wind shear increases, whereas the vertical velocity actually goes the opposite direction. It is decreasing in the low to mid troposphere as we increase the magnitude of the vertical wind shear. So that we actually observe like an opposing mechanism between increasing cloud fraction and decreasing vertical velocity once we impose the vertical wind shear into the convective system. And we can see that even more clearly if we plot the domain average updraft velocity and updraft fraction. So going from L1 to L9 case, despite the varying temporal trends, we can see that the updraft velocity generally decreases as we increase the vertical wind shear magnitudes. And in terms of the updraft fraction, there is a very clear divergence between L1 to L6 case and L7 to L9 case. And where so the updraft fraction increases almost monotonically as the wind shear magnitude increases. So this interplay between changes in mean updraft velocity and fraction explains this non-monotonic convective response we observe in this model. And you may wonder, like, why the cloudy updraft mass flux behave the way it is. So if we look at the updraft velocity, we further look at the vertical momentum budget of this cloudy updraft. So the momentum budget can be written as the combination of those terms. And we also computed the buoyancy-induced perturbation pressure and dynamic-induced perturbation pressure. What we plotted on the right is actually the cumulative contribution of each term to this total vertical momentum budget. And we show the results for the control simulation and the L6 case at both 30 minutes and 90 minutes. So I just want to draw your attention to two curves. So one is this green curve. This green curve is basically the effective buoyancy term that determines like how fast like the cloudy updraft goes in the atmosphere. That is the positive acceleration. So we can see that this effective buoyancy term is relatively similar between control and L6 case at both 30 minutes and 90 minutes. And what's most different is actually this purple curve. This purple curve is dynamic perturbation pressure. We can see the biggest difference in dynamic perturbation pressure specifically at 90 minutes between control and L6, because at L6 case, this dynamic perturbation pressure becomes much more negative compared to the control run. And this shows that once we run this simulation, the dynamic perturbation pressure is going to become more negative once the convective system is subject to the vertical wind shear, and that is going to deaccelerate this cloudy updraft. Okay. And why the cloudy updraft fraction becomes larger while the dynamic perturbation pressure becomes more negative? We think this is actually related to the cloud morphologies. Once we impose the vertical wind shear to this convective field, it's going actually to change the cloud morphologies. For the control simulation, is it working? It's not working. The animation doesn't play. Doesn't
Is it
work.
Google Slides you using? Or is it
No,
Google
it's a PowerPoint.
Oh, then I need to download it and
Oh,
PowerPoint.
okay, that's fine. Well, anyway, you are going to observe an upright cloud, which is circular. You can imagine that. And then if we look at the linear simulation, then you can actually observe the clouds. They are actually developing in a more linear and also stretched way, which is also more tilted compared to the control simulation. And we think this change in cloud morphologies change both the cloudy updraft fraction as well as increasing this downward dynamic perturbation pressure that is going to deaccelerate the cloudy updraft. And this actually creates an opposing mechanism between the two. And that's why we observe like a minimum mass flux at a moderate vertical wind shear profile. So this is the conclusion. Yeah, so we actually observed the non-monotonic behavior of the convective response with the imposed vertical wind shear. We think is primarily driven by the updraft mass flux and condensation rate, and we also tries to use this opposing mechanism between updraft velocity and updraft fraction to explain this non-monotonic behavior. And you might wonder, like, do we observe organization to occur more often under certain vertical wind shear profile? Unfortunately, no. For this particular model setup, we think this might also be related to the 500-meter resolution that we use, which is still too coarse to resolve entrainment-detreatment process explicitly. And we also want to explore different like wind shear setups. So we're also like different sea surface temperatures, work different microphysics schemes, so that we might be able to observe convection to occur more robustly. And this will be investigated in the future. Thank you so much for your attention. Sorry that the animation doesn't work.
Yeah, so
It actually looks fine. Yeah.
Could I make a comment?
Yes.
The shear profiles you used there were typically for mid-latitudes. For tropics, it's very different. And certainly the momentum flux would be very different for the tropics. I mean,
Yes.
this constant shear, literally.
Yes. Yes.
And that is a very big, the organization you get from that sort of situation is very, very different from the tropics.
Yes, I know. Yeah, we actually tried various different like wind shear profiles, including a very typical like wind shear profile from tropics. But the reason we use the linear is one reason is because we think the convective response is actually the strongest when we impose this particular wind shear profile. And the second is we think this linear can probably result in some theoretical relationship, which is simpler, so that we can include in the CAM model. That's why we actually
You can do it theoretically for both places.
yes, that's true. We actually also try like different we try also like different like a shape like U shape and other shapes, which is typical of tropical atmosphere. But
You see a big difference, for example, with the Julian oscillations and things like that. Larger scale organization be very different.
But one thing that I forgot to mention is that like this vertical wind shear, we actually don't impose directly at the surface. We actually also elevate this vertical wind shear to above the boundary layer so that it minimizes the shear cold pool interaction. Yeah, so maybe that's the reason that we actually don't observe the convective organization, but we want to understand like what the impacts of the tropospheric wind shear have on like the convective development. Yeah. So yeah, thanks a lot for the question. Yeah, I actually tried different profiles. Yeah.
Hi, Yang. I have a question for you. It's a nice talk. Can we use this model, SAT model, but apply more realistic wind profile in the model? For example, the wind of the QBO
Yes, for
and
sure.
see
You
the
can.
response of the convection to the QBO wind.
Yes,
Sure.
yes. So even though it is an ideal, well, it is an idealized model, which means that you can actually impose any kind of wind shear. As Mitch just mentioned, you can impose like the typical tropical wind shear profile or like the QBO wind shear profiles, which is totally fine.
Okay,
Yeah.
thank you.
Mhm.
All right, I have your animation here, but the system is not allowing me to share some outside of Chrome for some reason. Apologies for that.
That's a pity. That's fine. It's okay.
All righty, so next up, did you want to use your own laptop or you want to use this? Okay. Next up, hang on.
Yes,
There we go.
cool.
This is the first slide? Yeah.
Yes. Well, my name is Hing Ong. Thanks a lot to NCAR CGD for the travel support so I can be here. Disclaimer, this work is totally independent from my hosting institution. Thanks a lot to my collaborators, Adam and Dayang. So I'm going to talk about double ITCZ bias and the non-traditional Coriolis terms. Well, double ITCZ bias has been a problem in many generations of Earth system models, and has been studied. Hey, these were disappeared, but has been studied for decades. These are just examples of 1995 to recent studies, recent projects. And I also mentioned non-traditional Coriolis terms. Most of the global atmospheric models share a common approximation, which is the traditional shallow atmosphere approximation. Using this approximation, we neglect the non-traditional Coriolis terms. Non-traditional Coriolis terms arise from planetary rotation, and it turns eastward motion upward and upward motion westward, and vice versa. It's also related to, you can think of it as a planetary vorticity in the northward direction. And I've talked about that we omit the non-traditional Coriolis terms in models. But here's my previous study. I use a linear idealized model and force the model with a prescribed heat source that looks similar to ITCZ. And I want to know, what is the flow response to that heat source? And here's the result. This is a meridional vertical cross-section of the zonal wind field in contour and the difference of zonal wind field with and without the non-traditional Coriolis term. Basically, I'm looking at the bias introduced by omitting the non-traditional Coriolis term in the shadings. So we see subtropical jets, which is promising. But we also see this red color, which means zonal wind bias due to omitting the non-traditional Coriolis terms, which sits right on the ITCZ. And in this linear model, that ITCZ that westerly wind bias is 12% of the subtropical jet. And here's my hypothesis. What does this zonal wind bias can further change the model, further change the, for example, the precipitation field? First, we think about vorticity tilting. ITCZ. Well, if we have a northward planetary vorticity sitting at the ITCZ, and ITCZ is going to tilt that vorticity, we will have downward vorticity in the north, upward in the south. And so neglecting that vorticity tilting is going to introduce enhanced cyclonic vorticity on the poleward side of the ITCZ and reduced cyclonic vorticity on the equatorward side of the ITCZ. And that is going to, I hypothesize this, that is going to enhance Ekman pumping in the poleward side of the ITCZ, which further enhance precipitation. And how do I verify this? This is not going to happen in my linear model with prescribed heat source. So I have put the non-traditional Coriolis terms into the MPAS model and use that MPAS dynamical core to drive the CAM model. And I run, for simplicity, I run the aquaplaning simulation with the QPC6 configuration, that is perpetual equinox forcing and fixed sea surface temperature. I spin up the model. What's this? I spin up the model for 1 year with motionless atmosphere and branch the simulation into two 16-year simulations, one continuing with the deep atmosphere equation with the non-traditional Coriolis terms, one without that. Here's the result. This is the precipitation climatology. We see one ITCZ sitting at the equator. This is the difference. So I call it bias because we don't have observation for an aquaplanet. So I'm taking the less approximated simulation, which is the deep atmosphere simulation, as the truth. And this is the bias of precipitation climatology due to the traditional approximation, neglecting the non-traditional Coriolis term. We see red color in the off-equatorial area, meaning increasing precipitation. Blue color at the equator, which means reduced precipitation. And that reduced precipitation is 20% of the ITCZ precipitation maximum. And why is this happening? Well, we look at similar meridional vertical cross-section of the zonal wind field. Again, contoured is the total zonal wind field. We see, again, subtropical jets. And the shading is the difference, is the bias due to not introducing the non-traditional Coriolis terms. We see this is similar pattern as my linear model. If we compare this further to the stream function, the contoured here is the total stream function, which is still showing Halley cell. And the shading is a difference. But let's first look at the contoured field. If the stream function is increasing toward the north, like here, it means upward motion. Upward motion is going to introduce a westerly wind bias when omitting the non-traditional Coriolis terms. So this is consistent with my theoretical study. And also downward motion here because stream function is decreasing toward the north. And blue color here means an easterly wind bias. We can check everywhere. Basically, it's consistent with my linear and linear model results. But what's not shown in what the linear model doesn't capture is the stream function difference. My linear model doesn't include Ekman pumping. What does Ekman pumping say? There's a zonal wind bias, well, when we look at the horizontal shear of the zonal wind, and we will see that there is a cyclonic shear bias, right? This is cyclonic, right here. Also right here. That introduces Ekman pumping, which is indicated by you see the shading here. It's in the stream function increasing toward the north, which means excessive vertical motion right here. That's due to the Ekman pumping. So I'll conclude later, but I also did the AMIP simulation with similar setting, like turning off the non-traditional Coriolis in one simulation and turning it on in the other. And this is the annual precipitation, and this is again the difference. Okay, this is AMIP simulation, so I'm not calling this bias. This is a difference due to introducing the non-traditional Coriolis or not. Again, omitting the non-traditional Coriolis increase the precipitation in the off-equatorial tropical area like these red colors, and reduce precipitation at the equator. So here's my conclusion. Climate model has been suffer from the double ITCZ bias, and climate models also have been neglecting the non-traditional Coriolis terms for decades. And this study showed that neglecting the non-traditional Coriolis terms promotes a double ITCZ pattern through this pathway. When neglecting the non-traditional Coriolis term, it enhances cyclonic vorticity on the polar side of the ITCZ, which enhances Ekman pumping and then enhance precipitation. And the opposite is true on the equatorial side of the ITCZ. That's what I have. I'm happy to take questions.
Okay. Plenty of time for questions. Yeah, I knew Rich would raise his hand.
Yeah. So all your simulations, at least on the campsite, I presume are 1 degree, 100 kilometer simulations, which we have a double ITCZ. But when we got a high resolution, it gets even worse. So would there be a dependence in this term in the way it's calculated on high resolution?
In the linear model, it shouldn't,
Right.
but it may be something else.
Right.
Like our convective parameterization is well tuned for lower resolution.
Yeah.
And we may be compensating some of those bias in the lower resolution model. And that tuning doesn't work for higher resolution. Maybe that's my guess.
Do you think the calculation of these additional terms would have any impact on that? If you were to do it on a high resolution?
I don't know, because the model is well tuned.
Okay.
I guess related to that, okay, what's surprising about the non-Coriolis, the non-traditional terms is that I wouldn't think vertical velocity would be particularly large, so I would think it would be a small effect. But I don't know, maybe 25 kilometers is large enough to start making a
Actually,
difference.
if you do a scale analysis, larger vertical velocity doesn't help. It actually needs longer time scale for that difference to develop. It's a slow effect, not a fast effect.
I was just curious. I mean, I assume the reason we haven't been doing this before is just to save computer time. So, like, did you notice any impact on the cost of the model, or was it negligible for your?
Which model, I guess?
Well, like you ran with the full Coriolis terms and the non. Did you notice any difference?
Okay. If I run this with the default, so it's basically the difference between MPass and other dynamical core.
Okay. Yeah. So you didn't do an MPass without the full Coriolis terms and MPass with the full Coriolis terms.
This is MPass without an MPass with, and the difference is negligible.
Okay. That's why. Yeah. That's what I was trying to get at. Cool. Thanks.
you're also making deep atmosphere approximation, is that correct?
Deep atmosphere equations.
Yeah, so like your cells are going out like that.
Yes, so my grid cells are not columns, straight columns. They are cone-shaped. They're upside down pyramid with whose apex is at the center of the Earth.
So did you make any changes to CAM physics because that has the shallow atmosphere approximation?
That's the good question. No, I don't. I haven't done any change to the CAM physics. I only changed the CAM to MPass interface.
Mhm.
Yeah.
Okay. Okay, any more questions?
Well, what would you think would impact the physics just by having effectively, I understand, just changing grid cell area with height?
Mhm.
So you're wondering if if the physics knows anything about grid cell area, and if it does, then you'd have to do something with the physics. Is that the basic idea?
I don't think it matters much, but the energy integral, any integral in physics relies on the shallow atmosphere approximation. They would just be slightly different. On the other hand, there's not much energy high up because the density is so low, so it probably doesn't matter too much.
So yeah, even your mass weighted vertical integrals, now you'd have to take into account the changing area. Okay.
Yes.
So, but where it starts mattering, the density is so low that. So,
So
what do you think, Hanli? I don't think it would matter too much, but
Yeah, I don't know. You can do a quick scale analysis. I think everything is about, accounting the shape change, the Coriolis force, and the variable gravity. It's about 10%. That's as Hing was talking about. And the specific shape change, I don't know, that may change if you kind of dilate or dilute the atmosphere a little bit at each level. So that may have some impact on the pressure gradient.
and it's always in the same direction. So it's
Yeah.
bias.
So about the energy conservation or momentum, I can only ensure that in the MPass dicore right now. And for a scale analysis about the shape change, this is low top atmosphere model, so it really doesn't change much. Although I included the whole deep atmosphere equations to ensure angular momentum conservation. But the only term that matters according to scale analysis is the non-traditional Coriolis term.
Okay. So I did some analysis of MPass dicore a while ago. Like when you run in Hell-Suarez forcing, you can check if angular momentum is conserved, and MPass was not doing very well. So you're saying that it would do really well now with the
No, it wouldn't. It wouldn't be improving.
okay.
It's
Right. Well, thank you. A little bit ahead of schedule, but that's not the worst thing. So next up is Yang.
Yeah, Yuan Pu. I would like to share my presentation on my computer.
Yeah, I was just thinking, since we're recording, it might be best to use this laptop.
Yes, okay. The PDF version of the file, some figure cannot show.
Oh, okay. And the problem is I can't share anything outside of Google Drive, so kind of stuck
So I
here.
was gonna ask, what's like the battery condition on that? Because it was near death. Like,
Oh,
this, yeah, right.
thank you.
Yeah, no problem. That's just.
I'll try and fix
Yes.
The recording will capture.
it. Will capture?
Oh, it will capture.
Because
Okay.
it captures remote presenters.
Yeah, so I can share
Okay,
from my
good point.
computer.
Yeah, thank you.
Hi, everyone. My name is Yuan Pu Li. I'm from CGT. I'm a postdoc here. My supervisor is Jack Chen. And today I'm going to talk about the mechanism in regulating the quasi biennial oscillation in CSM and E3SM. This presentation has 4 sections. First, I'm going to introduce some background information, like how the deep convection scheme drives the gravity wave scheme, which is very responsible for the QBO generation. Second, I'm going to introduce an important fix in the gravity wave scheme that is now integrated into the CSM. The code fix is done by me and my supervisor, and the QBO tuning is done by Major and Martina. Major is working on the wall cam, and Martina working on the middle top. So they are going to tune the QBO. And third section is QBO. We take the E3SM version 2 as an example to show the QBO is very sensitive to the change of the tropical convection variance. In the 4 sections, I'm going to explain a hypothesis that the Kelvin wave and mixed Ross wave gravity wave in the stratosphere can be partially intensified by the dissipation of parameterized gravity wave. I think it's a mechanism which is less understood, so it's a little bit challenging to explain that, but I will try my best. So first, the introduction of the QBO. QBO is a quasi-biennial oscillation in the stratosphere. From the observation, we can see the westerly and easterly wind regime propagate downward from the upper stratosphere to the lower stratosphere with a period about 28 months. The QBO is driven mainly by 2 forces. One is the gravity wave drag, which is parameterized in the model. Another is the large-scale wave, which is resolved in the model, such as the Kelvin wave, MRG wave, etc. And why QBO is important? Because based on the previous studies, QBO can influence the troposphere through different pathways. For example, by influence the deep convection in the tropical region, MGO, monsoon precipitation, and the QBO can influence the stratospheric polar vortex by the Horton-10 effect. And so we expect QBO can provide some predictability to the tropical troposphere, but it's still challenging because some other mechanisms. At first, we have to improve the QBO representation in the model. So here I'm going to introduce. Here I'm going to introduce the workflow from the deep convection scheme to the gravity wave scheme. So the deep convection scheme, which is the ZM scheme, will generate the heating profile, and then the gravity wave scheme will take this heating profile and use this to driven the gravity wave spectrum. And from the heating profile, we can get 4 very important parameters. First is the frequency of convection, and the second is the depth of convection, which is the depth between the top of convection to the bottom of convection, and U, which is the mean horizontal wind averaged in the convection, and the maximum heating rate, which measures the intensity of the convection. And the frequency of convection, you can think is just the time steps of convection. And D and U, that's depth of the convection, and the wind in the convection will determine the width and the shape of the gravity wave spectrum, which is this part, the shape and the width of the gravity wave spectrum. And the maximum heating rate will determine the amplitude of the gravity wave spectrum. It's very important to know that the amplitude of the gravity wave is proportional to the square of the maximum heating rate, which is very important, and I will explain later. And here, let's move to more important and interesting part. I'm going to talk about the fix in the gravity wave scheme, which is the impact of the net heating in the middle of convection heating profile on the QBO. Here we have 2 heating profile, and in a single convective time step in CAM. On the left is more common one, in which the heating rate is positive along the altitude, and this is very common and normal, and along with our assumption. And on the right is the situation that caused a problem, because you can find that there is a negative heating profile, there is a negative heating level in the middle of convection. That caused a problem in the gravity wave scheme, because when the gravity wave scheme have to detect the top of convection. According to the current algorithm, it will search the convection top level by level from the lowest level or from the bottom of convection. So when it meets the negative heating level, it will detect this level as the convection top. And the maximum heating rate is the maximum value between this range from the top and the bottom. So if the convection top is incorrect, then the maximum heating rate is highly underestimated, like the arrow, like the gray arrow shows. The gray arrow shows the old scheme, how the old scheme treats the profile, and the red arrow shows how the new scheme treats the arrow. The new scheme is this modification that will search the convection top from the model top, so it will catch the correct convection top and then capture the right maximum heating rate. This kind of situation, it became more frequent in the newest CAM. For example, this kind of things can account for 13% in the total convective time. But I think in the previous version or the old version of CAM, this situation is very rare. So the gravity wave scheme can work very well. And however, because this situation became more frequent, and now in the newest CAM, the gravity wave spectrum is incorrect. So even though Medium takes a lot of time to tune the QBO, but we cannot get a perfect QBO. But with this bug fix, it's not a bug fix, it's just a fix in the gravity wave scheme. Now Medium almost gets the realistic QBO in the wall CAM and also in the middle top of CAM. And so this slide, I'm going to explain to you why this negative heating level comes from. And this is on the right is the net heating profile, and which is made up by two parts. The yellow one is latent heating. It's almost positive, and the evaporation heating. The evaporation heating, you can see there is negative level in around 600 hectopascal. Rich explained that to me, that because the ring drop fall down from the convection, and when it meets to the 600 hectopascal, it will evaporate and cause the negative heating. So it will contribute to the negative heating, the net heating, and the DM and the gravity wave scheme will use this net heating profile to calculate the parameters used to driven the gravity wave drag. And here is compares the change between two different gravity wave scheme. The blue one is the old one, which is without the fix, and the orange one is a scheme with a fix. So we can see there is very important change in both the maximum heating rate and the depth of convection. You will say, okay, these two lines are almost identical, but please notice the head of the red line. This part is considered as very weak convection in the old scheme, and it accounts a large part of the convection time step. But now this part of convection is corrected, and so this part is fall down to the orange line, and the orange line, the tail of this curve has get a little up from the blue line. So, and another thing is the amplitude of the gravity wave drag is proportional to the square of the maximum heating rate. So it will have more important influence on the gravity wave drag and QBO. And another thing is the edge depths, the depth of convection also change dramatically. It will change the shape and the width of the gravity wave spectrum. So it will change. The mechanism is is not easy to explain, but it also will change the QBO. And so here is the output of the QBO. On the left is the QBO from the old gravity wave scheme, and the right is the QBO from the new gravity wave scheme. You can see these fix intensify the QBO dramatically, and but the QBO still need to be retuned according to by other tunable parameters. So, but what we can get from here is this fix in the gravity wave scheme will strengthen the QBO dramatically, significantly. And here is the same thing, but in the E3SM. E3SM also has this problem, and E3SM, this kind of situation, the negative heating in the middle of convection, this situation accounts for 27% in the total convective time step. So it's more important to E3SM. So here is a change in the PDF curves in the E3SM, and you can see it's changed the maximum heating rate PDF dramatically, and other things also changed dramatically. So the QBO is also strengthened in the E3SM with this gravity wave fix. The conclusion here is this new fix overcomes the underestimated maximum heating rate issue. And this fix intensifies the QBO amplitude and shortens its period. And based on this fix, now the newest CAM is able to achieve a more realistic QBO by tuning. This is done by Meijun, and Meijun is going to give a talk tomorrow. And here is the third section. It's not related to the previous one, but I'm going to explain how QBO is sensitive to the change in the tropical convection variance. Take the E3SM version 2 as an example. Why we started this? Because in the E3SM version 2, we have a new update in the deep convection scheme, which is called DCAPE. I won't jump into the DCAPE because I'm not expert in the deep convection scheme, but the DCAPE just to put more dynamical constraints on the occurrence of the deep convection. Anyway, I'm interested in how this update in the deep convection scheme will influence QBO. On the left, you can see with this update, the QBO is getting stronger compared to the version without this update. Without this update here, the QBO is very weak, almost disappeared. But with this update in the deep convection, the QBO get much stronger. And here I'm going to explain why. First, I'm going to check the frequency of convection in two different simulations. Here you can see with these constraints of the deep convection, the convection deep convection appears less frequent. And here's the simulation with the update in the deep convection. And that's a part of the issue. Another issue is at the same time when the convection became less frequent, the convection became more intense. We can see from this PDF change in the maximum heating rate. You can see the new the update one, which is the blue one, makes the maximum heating rate more intense. And when we look at, but we have to consider the frequency of convection and the intensity of convection together. So here I'm showing the climatology of the maximum heating rate, which shows that this parameter almost identical in the two different simulations, but is deceptive because the QBO and the gravity wave drag is driven by the square of the maximum heating rate. So we have to calculate the climatology of the maximum heating rate square. Here you can see the blue line has increased significantly from the orange line, and this represents the variance of the convection. And so we can see in the E3SM version 2 with its update to the deep convection scheme. The convection became less frequent but more intense, so the variance of the convection increased. So the gravity wave drag and the QBO is stronger. Okay, that's the conclusion. And here is the fourth section. I'm going to explain a hypothesis that the Kelvin wave and mixed Rossby gravity wave in the stratosphere can be intensified by the dissipation of the parameterized gravity wave. It's more about the mechanism. And here we compare two simulations. In one simulation, we turn on the gravity wave scheme. And in another simulation, we turn off the parameterized gravity wave. So we just compare the difference between these two simulations. And here is the zonal wind at 45 hectopascal, the Wheeler-Claudius analysis. Here shows the difference. You can see with the gravity wave, the MRG wave and Kelvin wave is much stronger in the stratosphere. And we think it's caused by the gravity wave scheme, the dissipation of the gravity wave. Here's more evidence because here we separate the background wind as the easterly wind and westerly wind and do the composition analysis in two different periods. We calculate the momentum flux, which is rho u prime, the omega prime, and we separate different waves like Kelvin wave, MRG wave, and we calculate the relative enhancement of the Kelvin wave in the stratosphere compared to its input from the tropopause. And here we see in the easterly QBO phase, the red line represents the simulation with the gravity wave dissipation, and the blue line is when the gravity wave scheme is turned off. So you can see, compared to the input from the tropopause, Kelvin wave is intensified in this region and in the easterly QBO phase, not in the westerly QBO phase. In the westerly QBO phase, MRG wave is relatively enhanced in this region compared to its output, compared to its input from the tropopause, and because I said it's normalized by the wave momentum flux from the 96 hectopascal. So there's evidence that planetary wave is intensification is present in the stratosphere due to the dissipation of the parameterized gravity wave. But I have to say, this mechanism is not fully understood and needs more theoretical works. We are going to use the Wachem nudging method to fix the background wind to see how the dissipation of the gravity wave will contribute to the intensification of this large-scale wave. It's a little bit complicated, but Kai is also helped me to work on that. So in the future, we are going to explore that. And here's the conclusion. First, we have an important gravity wave fix in the gravity wave scheme that is now integrated to the newest CAM and Wachem. And we are going to preparing a paper. And the second is QBO is sensitive to the change of the tropical convection variance. Third is a hypothesis that the Kelvin and MRG wave in the stratosphere can be intensified by the dissipation of the gravity wave. So this paper has some stuff related to this conclusion 2 and conclusion 3. And thank you very much.
Yeah. Questions for Young Boy?
Just a quick question. With the changes in the convection scheme, did you check it against the effects of the organized convection parameterization?
Oh, I haven't.
Mm-hmm. That might have an effect, you know.
Yes,
because it changes the depth of the convection as well, and the occurrence of convection. You know what I mean?
Yeah, I know. I got your point. It's a very good question. And Jack and I is going to test how the update in the mesoscale convection will influence the QBO, because now we have this bug fix. First, with the bug fix, we can capture the right maximum heating rate. Now, Jack is just to instruct me to see the difference between the update of the mesoscale convection.
MGSP,
Yeah,
yes, yes.
how it will influence the QBO. It's a very important question, and we are working on that.
Very good. One more question. Does the Kelvin wave strength and amplitude affect this at all?
Yeah.
Okay.
Yeah, Kelvin wave intensification influence that.
I
Yeah,
see.
very important.
That's another point about this organized convection side. It's stronger Kelvin waves too. So
Yeah, I'm going to test about that.
that'd be nice. Thank you.
Yeah.
Yeah.
Because only, oh, sorry.
No, go ahead.
Well, Kelvin wave is very important, but Kelvin wave is not enough to driven the QBO. So Jack tested this mesoscale convection update on the QBO, but he didn't say anything because only Kelvin wave intensification is not enough to driven the change in the QBO. But
Nice.
now with this fix, we can test everything. Yeah.
Nice. Thank you.
Julio has a question?
Oh, Julio has a question. Hi, Julio.
Hi, thanks. Nice talk. I just wanted to follow up with you about this idea that was raised a while ago about fitting some sort of profile to the heating instead of just using the max diagnosed from what ZM kind of spits out. We try to fit a profile, and that might have an effect on Qmax, since we really don't know how the ZM heating profile relates to what's actually generating gravity waves in convection.
Yeah, if we have more resource, I would like to review how the gravity wave is generated by the different heating profile, because now we have MPath, cloud resolved
Right.
model, many tools. This gravity wave scheme is based on the Yagas research decades ago. So we have new tools, but if we have more resources, I would like to check that.
Yeah, I think it's time to revisit
Yeah.
that issue. All right, thanks.
I agree.
Great, thank you. So Fiona Shaw next. Your PowerPoint now set for my computer here.
Okay, thank you.
If you have animations.
Great. Hi, I'm Jonah. I'm a graduate student at CU, and I work with Gen K there. And I am, I guess, more on the evaluation and diagnostic side of thinking about climate modeling. And so I'm going to talk about a tool that I developed and then put in CESM. And this is kind of a pitch, I guess. But I'm going to focus on trying to motivate like why we did this and why I hope it'll be useful, and leave hopefully a fair bit of time at the end to talk and like hear what, as like the CAM developer community, what your thoughts on this are. So a little less than a year ago, we had a CLIVAR meeting in Boulder that was about confronting our system models with observations. And this was a really great meeting, and it had this fun little tag about confronting, as if, you know, there's some kind of conflict, but also that there's good, bad, and ugly things about the way that we are evaluating our models. And the very first talk was given by Gavin Schmidt, who's the director at NASA GISS, and it was about kind of learned lessons from a long time of doing these comparisons. And Gavin made one really good point, which he called a philosophical footnote, which is basically saying that all observations and comparisons are based on models too, or in other words, it's models all the way down. And so the idea here is that, you know, we're working in model world and we take in observations, and we often are so focused on the modeling that we're not maybe interrogating the structural uncertainties that are present in those observations. And so those observations themselves, there's a huge kind of chain of procedures that get them to us in this nice gridded format. And so we should be skeptical, or maybe have some kind of quantification of uncertainty with the observations that we use. And so I'm just going to give a few examples that I think are hopefully relevant to folks evaluating atmospheric models. The first one is CERES. So CERES, again, is this collection of instruments that measure broadband, shortwave, and longwave radiation at the top of the atmosphere. And these are like pretty essential, I feel like, a first order constraint on model behavior. But something to note is that CERES actually observe radiation over a very specific solid angle. So it's not actually observing a flux, it's observing a radiance, and they have to report a hemispherically integrated flux. And so what that basically looks like in a very simple diagram is that we're only observing at any kind of single point is a sliver of the hemisphere of the energy, and we need to basically apply some kind of model to get this hemispherically integrated value of our outgoing long-wave radiation or reflected short-wave radiation. And this is called an angular distribution model. And Ceres works incredibly hard to do a really good job with these models, but it's just a reminder that Ceres observations are in themselves models. Furthermore, these Ceres instruments are not kind of perfect radiometers. They don't have a unitary spectral response function. They respond to radiation differently. And so there's effectively another modeling step, which is deconvolving the observations to try and estimate what the true broadband fluxes are. And so just thinking about it, even with Ceres, we should have some appreciation of the uncertainty in those observations. Another great example is with reanalysis and satellite observations. So what I'm showing here is trends in atmospheric water vapor that are obtained in the top row from 3 different retrievals that are all using the same set of observations. So these are observations from NASA's AIRS instrument. It's on the Aqua platform that's been up since 2002. And so effectively, all of these retrievals use the same exact input. And you can see that in this top row, they look dramatically different. So even when we're feeding the same exact observations into retrievals, we're getting different answers. And so this process of inferring a state variable from an observation, which again is this radiance term, is a very uncertain process. In the bottom row, we have ERA5, MERA2, and a CMIP6 average. And the idea here is that reanalysis, of course, is ingesting more information than just this one satellite, but you're also getting very different answers. And so this is, again, a good point that it is models all the way down. So these reanalysis and satellite products are differing even when they ingest the same direct observations. And this is really just implies really large, or I won't say really large, but a unquantified structural uncertainty in these data that we rely on really heavily to evaluate our models. And so I think a really good point to make here is that a lot of the information that we have on the atmosphere comes from the satellite record and specifically comes from infrared sounders that are observing specific spectral regions. And even though there's structural uncertainty in the retrievals, those observations that the retrievals are based on are really well calibrated and are actually an incredibly robust record. And so I think what we need to think about, especially when we have reason to be skeptical of these data sets, is why not compare models directly with those observations, with basically the level 1 radiance observations. And there's a few reasons why this is difficult. One of them is that these observed radiances are not something that a model is going to compute. The rate of transfer model in CSM produces heating rates, it produces very coarse spectral fluxes, and it's meant to iterate the physics as best as possible, as cheaply as possible. And what we observe are these fields that are specific to an instrument, really the way the instrument was designed and how it responds to different wavelengths of light. And also it's specific to the way that these satellites are doing their sampling. So a lot of these instruments are polar orbiting, they only observe twice a day. And so we have these definitional differences that hinder fair comparisons. But hopefully the tool that I've built can really help make these comparisons with these direct observations as easy as the comparisons that we're already doing with Ceres with those reanalysis products. And so, yes, I do think we can make these comparisons easier. And I'm going to give an example with 2 NASA missions. On the left, this is AIRS, or I guess it's the Aqua platform that has AIRS on it. This instrument has a more than 20-year record. It's incredibly valuable, and it covers a huge part of the infrared spectrum. So there's just a lot of information about the entire atmosphere in AIRS observations. On the right, we have a more recent mission called NASA PREFIRE. These are 2 CubeSats that are measuring spectral radiation, I think between 5 and 50 microns. And I know that we don't think about maybe wavelengths here, but the idea of this mission is that our record of infrared sounders ends at about 15 microns, but a huge amount of the Earth's emission is contained in those far infrared wavelengths. And so we haven't systematically measured them beyond kind of what we can infer from those broadband fluxes. And so this is a very different mission from AIRS. It's 2 CubeSats. They've just gone up. They won't be up for 20 years, but we want to be able to leverage that, those observations. And a lot of the motivation actually for this mission was to provide a constraint for Earth system models. So this tool is called, I call it COSP RTTOV. It's not a great name, but you're hopefully all familiar with COSP. And so I just tacked on another acronym there. And so we basically start with CSM2 or any Earth system model, but right now it is, I believe, only implemented in CSM2. You know how this works. And then we think about COSP. If you're not familiar with COSP, it's a satellite simulator package. It basically reads in the model state and runs it through these satellite simulator programs that generate satellite-like values for cloud fields. So we can get a MODIS-like cloud fraction or a Calypso-like cloud phase fields. And these have been really valuable for evaluating CSM in the past. And so the only thing that we're adding on here is a radiative transfer model, RTTOV or RTTOV. And what this effectively is that whereas RTMG produces fluxes for iterating the physics of the model that aren't comparable with these direct observations, RTTOV is made to emulate those observations directly. And so effectively, COSP is just our middle step to transfer the model state into this additional radiative transfer tool that then produces satellite-like radiance fields or brightness temperatures that are basically level 1 equivalent fields. It's pretty fast. We've basically validated against the model. I won't show that here, but I'm happy to talk to you about it. And it simulates all sky and clear sky fields with the idea is that we want to leverage the observations as much as possible. And so this is just an example of what output looks like here. So on the left, we have a brightness temperature, which is just a radiation field moved into a temperature space, and it's for a channel that is in basically the window region. It's the most transparent channel on the AIRS instrument. And on the right, we have CSM2 surface temperature. And so the idea here is that these satellite spectra, like there's a reason that we all work with state variables when we're evaluating models, and it's because these spectral fields can be non-intuitive. But when we work with the folks who have a lot of precise knowledge about what these fields mean, we can actually do our evaluations in this direct space where, again, there's a lot less structural uncertainty. So basically, I'm just showing that this spectral field is almost a 1-to-1 comparison with surface temperature. Of course, we can look at things that aren't surface temperature. And so we can think about a field that samples the upper troposphere and compare it with CSM2. We don't get a 1-to-1 comparison here because, again, these fields are not, it's not this isn't a temperature retrieval. But the idea is that the actual variance in the modeled field is contained in the satellite-like field that we're now emulating. And in the bottom row, we can take that clear sky channel that we looked at before and just take a difference between our all sky and clear sky radiation and get surprisingly a really good proxy for cloud fraction. So the idea here is just that we want intuitive meeting. We don't want to have to teach everyone to think in a abstract spectral space. And that, I know some about this, but the folks who've been working on these missions and working on their retrievals have an immense amount of knowledge and are really interested in leveraging these data for model evaluation and would be really excited to work on this. So now that we've kind of shown these fields and thought about their intuition, we can start to evaluate CESM. And so this is just looking at that channel that was sounding the upper troposphere, and we can look at the AIRS observations, and we can look at CSM2, and we can basically immediately identify a cold bias in the model. And so again, it's just as simple as that, is that we can make the same clear comparisons by comparing against direct observations and not relying on something that we're not sure how certain it is. If we look at a kind of another region in the mid-latitudes, we see, of course, much more of a seasonal cycle, and we can identify basically the same bias. And we can also, if we look closely, identify more of a winter bias than a summer bias. But the idea is just that we can do simple time series evaluation and kind of whatever evaluation you want to do in this space. Now we can also apply that to that metric for clouds. And we can see that in the tropical region, the clouds are actually captured really well by CSM2, but in that mid-latitude region, there appear to be not enough clouds in CSM2. And so the idea is just that we can do all of our kind of typical evaluation in this space. Another application for this is, again, this pre-fire mission. So these CubeSats are going to be up for just a few years. And so it means that we have this challenge of internal variability when we're evaluating them against the model. And so what we can do is simulate these satellite-like fields in a much longer record to basically create the context to put those observations in. So these are just, this mission is polar focused. So I'm showing some polar maps of different channels. The two on the right are in this region that we haven't observed. And then we have our time series. So we can basically construct the statistics of the model with this tool. And right now, I'm working with the team for Prefire to put together basically a gridded product of their radiances. And so we can immediately plug these kind of data with each other and start to evaluate the model against this new constraint. And another way, if we're thinking about satellite missions that Prefire is already up, but of course, new missions are always being proposed, is that if you're interested in working with NASA and they have a mission that is proposed, you can simulate their instrument or maybe multiple configurations of their instrument in the model and basically have all of that work that can inform the design of the mission and maybe identify strengths and weaknesses before it gets off. So these are called observing system simulation experiments, but we don't have these at a climate scale that are done, and this tool hopefully makes that a lot easier. So this is kind of what we construct from the Prefire record. And so I think that's where I'll end it here. The idea is that we're simulating satellite spectral radiation fields directly in CSM2 with the goal of avoiding structural uncertainty in kind of standard comparison fields. And I don't think this should replace the evaluation that we already do, but I think it should complement it, especially in cases where we have reason to be skeptical of those standard methods for evaluation. And we can also think about supporting satellite missions by simulating them ahead of time or simulating them. And this, simulating the direct radiation fields is valuable because this is a small mission and building out these retrieval products is a long, often a multi-year process. And so it makes it easier to interface with things. There's a preprint if you're interested, and I'm always happy to talk and get emails. Thank you.
Thanks. Questions? If you need help with acronyms, Jesse Nussbaumer here is an expert.
I'm gonna ask a question. This was like 2 years ago now or something, but we met for a little bit just because it was a little expensive to run these. Is there any update on that, or is it still kind of?
Yeah. So I guess we ran, this kind of goes well to this. Okay. So we've added some satellite-like swapping here. So it basically allows you to only run the simulator when the satellite would reasonably be overhead. So I input here the orbit times that the satellite is orbiting at, and then it only calls it at those times. So this has basically allowed us to reduce the number of calls to that additional rate of transfer model and cut down the cost of it. I think we can simulate about 45 channels from AIRS and do this swapping, and it is something like a 20% hit on atmosphere only CAM 2.1.5. I think I think there's like, when you're thinking about a large ensemble, you may be skeptical of this, but if you're doing single kind of sanity tests, simulations, I'm optimistic that this won't be an issue. And when we evaluated it, we ran it in SCAM, and we basically produced like tens of thousands of channels, and we integrated them over the entire hemisphere to validate against our RTMG. So there's like different ways that you can run it.
Cool, thanks.
Go ahead, Rich.
If you put it back, we showed the 6.5 part of the 3 products and then 3 reanalysis.
Oh yeah.
Early on, yeah. And I was wondering, like, Mera clearly decided to simulate, the ClinCaps, given that.
So they
product. Were they super excited and thought this is the one?
So basically, I'm not sure if they're assimilating ClinCaps. They're using the same prior in their retrieval.
Okay.
So that's why, yeah, you can see the structural similarities between ClinCaps and Mera 2. But the idea is that all of these retrievals probably use some degree of optimal estimation that's based on some kind of prior guess about what the atmosphere is looking like. In that, I'm not a retrieval expert, but that's a big reason why these are looking so different.
Just a technical question. Has your version of COSP compared to what we have in CSM, has that changed due to your modification, or is it still the same?
So I've updated the cost simulator F90. That's like, I've made some changes there. I'm working with, I've worked with Brian Medeiros on this, and we're pulling this into the kind of formal COSP branch as well too. I definitely, coupling this in to CSM is difficult because this radiative transfer model is basically I built it separately and then I link it during the build step. And so there's you can get it to work, but it's not like all the code is just sitting in CSM now. Yeah.
Okay, well, thank you.
Thank you.
So we have a break now for 20 minutes, and the refreshments are in the usual place in front of the main seminar.
Hey, Josie, you haven't had that.
Ding, 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 ding. Alrighty. Time for the second session here that will be started out with Vince Larson's presentation.
Great. All right. Well, thanks for giving me a slot to speak. I'll be talking about work that I'm doing collaboratively with Jun Guo and Ben Stevens. It's about impediments to model tuning, stubborn biases, tuning trade-offs, and nonlinear parameter dependence. Okay, so our problem is when a new and hopefully better parameterization is introduced into a global atmospheric model, typically the results get worse. And why is that? Well, the standard reason given is that compensating errors have been baked into the model by prior generations of tuning. And then when we introduce a new, hopefully improved parameterization, those compensations are disrupted and the answer gets worse. So what do we do? So I'd argue we want to do two things. First thing is we want to retune. And the reason we want to retune is to see if the new parameterization looks promising. I mean, ultimately, we want the new parameterization to outperform the old one, and it's not always clear whether that'll happen. So if we quickly retune and then it has promise, then we might want to get hints about what part of the model structure to change next. And so the philosophy here is basically that the big gains in the model improvement will come from changes in the model structure. In other words, in the functional form of the equations. But the tuning is also necessary, but we just want to get it over with as quickly as possible. So we want a cheap sort of approximate tuner for this type of problem. Okay, so the outline of my talk is first I'll introduce this tuner that we've been developing. It uses a simple quadratic emulator of Clam's parameter dependence. Then we'll show some example tuning results from a global atmospheric model, which is EAM, which is DOE's counterpart to CAM. Then I'll show two sort of archetypal model errors, tuning trade-offs, and stubborn biases. Okay, so we call our tuner quad tune because it's quadratic in functional form. What does it do? Basically, it adjusts P parameter values in order to match N regional metrics. So what do I mean by a regional metric? So a metric field is just it's an observation that you want to match. So in our case, it's going to be shortwave cloud forcing, so the brightness of clouds. But then we average it over regions. So here we're averaging over 20 degree by 20 degree boxes that cover the globe, and we want to match shortwave cloud forcing in each box. And in this particular simulation, you can see that these two stratocumulus regions are way too bright. So we want to tune that away if we can. Okay, so the recipe for tuning in quad tune is fairly standard. We choose our regional metrics, so shortwave cloud forcing in the 20 by 20 regions, choose our tuning parameters from the model, and then we run 2P plus 1 global simulation. So the one simulation is a default simulation, which we have to run. And then we perturb the parameters one at a time, and we perturb each parameter high and then low. And we have to do that because there's so much nonlinearity in the parameter dependence. And we keep doing that for the parameters, so we have 2p plus 1. So this is the expensive part. So we want to reduce the number of global simulations we have to do as much as possible. Then what we do is once we have those simulations, optimize difference between the model and obs using just regression, basically. And then we have some diagnostic plots, so that's cheap. But ideally, our goal is to be able to run all these global simulations overnight. So we just run a batch, and then the next morning we come in and look at the diagnostics. Okay. So here's sort of a linear regression view of tuning. So our tuner is quadratic, but it's kind of like this. So you can imagine schematically, we have 2 parameters, P1 and P2. And then that dots into this sort of design matrix, which is basically a sensitivity matrix. So each row gives you a different region, a different box over the globe. And the first row gives you the sensitivity of that region to 2 different parameters. And we want to find parameter values such that when we dot that into the first row, we get the bias here, and that will remove the bias. We want to do that for each row, for each different region. But of course, if we have more regions than we do parameters, we can't fit everything. Okay, so that's what we're doing. What does our emulator look like? So this is trying to emulate the global model's parameter dependence. We assume the global model has some biases. We assume, or some values of short wave cloud forcing. We assume if we change the parameters and multiply it by the sensitivity matrix, which is this thing right here, that then it'll change the answer somewhat, but we also add this quadratic term. Quadratic term, we ignore the off-diagonal elements because that will reduce the number of parameterization, the number of global simulations we need to do. So we end up with something like this. It looks like linear regression, but with this quadratic regularizing term. So it's like ridge regression. And that term sort of prevents the parameter value. It prevents the parameter values from growing too large, which is problematic. Okay, so yeah, the whole goal is we neglect the parameter interactions, which then, of course, makes the emulator less accurate. So we're not going to find Ham's true global minimum. But it makes it cheaper. We don't have to run so many global simulations. Okay, so here are some example tuning results. Why did we tune? Because we were introducing a new version of Club Taos. It was out of tune. Here we're going to tune for 5 club parameters. Each of our runs lasts 14 months. And we're going to attempt to match shortwave cloud forcing in all our boxed regions. This is our starting point. So here you can see these stratocumulus clouds here are way too bright. And we end up with an RMSE at 12.66, which is kind of middling. Then when we tune using quad tune, this is what happens. We don't get rid of the stratocumulus biases, but they're a little bit better. The RMSE is 10.4. Now for comparison, you can compare this with Jun's hand tuning, and that gives 10.1. And Jun is such a good tuner, I think we can regard that as the global minimum. So we're close to, it gets rid of some of the bias, but not all of it is the point here. So, okay, so quad tune, it helps reduce the biases in the stratocumulus regions, but there are other regions, these red regions, where actually the bias gets worse. And so we want to explore why that is. And so quad tune adds some diagnostics to try and give some intuition. Okay, so that brings up the question of what is quad tune doing? So what does quadratic regression do? And my interpretation is what it's trying to do is remove the really strong biases in the sensitive regions, and then it kind of ignores the other regions. So this plot is trying to illustrate that. What we're doing is basically taking this multivariate regression problem and trying to reduce it down to a univariate sort of form. And to do that, we take these sensitivities to the different parameters and we just compute the magnitude of this row. So we're saying, how does this region depend on all the parameters? And that's plotted along the horizontal axis. So horizontal axis is sensitivity. To the right here are the very sensitive regions. And right along this vertical axis is no sensitivity. Like you change the parameters and the metric doesn't change. Okay, then we plot that versus the bias. So basically that's the right-hand side here. And we're saying these regions are too dim, these are too bright. And then the color coding for this gives the residual bias. In other words, that's the bias after tuning. And so what do we see? So you can think about this as just univariate regression. You got scatter points. You want to fit a line through the origin, but also through these points. And what would you do? You draw the line straight through this cumulus over here. Okay, so that's what the model seems to be doing. It reduces those biases down to almost zero, but it leaves these biases basically unaffected or even worsened. And why? They have no sensitivity. They just can't be budged, or they're sort of on the wrong side. They're too dim instead of too bright. Okay, so that's kind of what it's doing. So QuadTune adds some diagnostics. So let me show some of these. So these are sort of the favored regions. Those are those points that QuadTune is insistent on fitting because that really, reduces the value of the loss function. So here's one of those regions, and there are 3 dots here. The middle dot shows the default simulation. So that's the value of C8, which is one of our parameters on that region. And then the 2 outside dots are the sensitivity runs. So we perturb C8 high, we perturb it low, we get these values. The orange X here is QuadTune's recommended parameter value. So it's what QuadTune thinks is a optimal value. I hope you can see my cursor. Yeah, okay. So you notice, for instance, in this region, it's interesting. N2 thresh, it's a parameter in club, never mind what it is, but it has a very strong sensitivity and it's linear. And so QuadTune sees that and says, this is wonderful. I can just boost N2 thresh a bit, and that will get rid of the bias in this stratocumulus region. I'm sorry, the red line here is the observations. So basically it's saying, if I want to go towards the red line, I've got to boost N2 thresh, and then I'm there. Okay, so these are just different diagnostics, and this is another one that QuadTune has, which is proven to be kind of useful. It's a graphical representation of this matrix equation that I showed before, essentially. So what it says is it takes selected regions. So here's our favored stratocumulus regions that it really wants to fit. Here's some other regions. And then it's plotting it versus normalized bias. So over here, these regions are too bright. And basically, these regions are too dim. So the vertical black line gives the bias in the original default simulation. The horizontal black line gives how much bias is removed by tuning. So basically what QuadTune thinks is, wow, these stratocumulus regions are way too bright, but I can reduce most of that by tuning back to almost zero here. And then the color coding tells you which parameters are doing that bias removal. So it's saying, for instance, this purple region is really large. And so this N2 thresh parameter is reducing the bias, it's dimming the clouds quite a lot. Okay, so basically what this is a visual representation of this matrix equation. So for instance, if you multiply these parameters into these 2 columns, this term right here is the length of that bar. This term here is the length of that purple bar. This bias here is the position of that vertical line. And then the next row is the next bar, and so on. So basically you have almost complete information about what QuadTune is doing in this graphic here. And then the beauty is you can kind of get a sense of which parameters matter where. Okay, so now let's look at some specific tuning trade-offs and stubborn biases that we found in this particular tuning run. So here is one, Bolivia. So that region is, it's this box here, this green box here. It's right next to the stratocumulus regions. That one has a positive correlation with the favored stratocumulus regions, but the wrong bias. So let me explain what I mean by that. So what I mean is these are the 2 stratocumulus regions that QuadTune really wants to match. And Bolivia is this other region. The key thing is that the sensitivities to the parameters are proportional to each other. They're similar. So that orange is like this orange. So that parameter behaves similarly. It dims. That purple is like this purple. Dims. That red is like that red. This blue is brightening like that blue. That green is like that green. So all the parameter sensitivities are the same sign, proportional magnitudes. And the point here is that no matter how you change those parameters, if you dim these stratocumulus in order to reduce those biases, you're also dimming Bolivia. But we don't want to do that because Bolivia is too dim already and we're making it worse. Whereas here, these are too bright to begin with. We do want to dim those. In other words, we want to bring these close to 0. Well, that makes Bolivia even worse. Okay, so the key point is you get some sense of why quad tune can't find the right tuning parameter. You just have a tuning trade-off. And you could imagine strategies. You could say, well, I don't care about these stratocumulus biases. I care about Bolivia, so I'm going to tune the parameters differently. You still have the trade-off, but it tells you kind of what your options are. Okay, so that's one type of pathology we noticed. Another one is sort of the opposite problem. I had the right bias, but the wrong sensitivity. So let's look at that one. Okay, so that's Siberia here. It's too bright. This vertical line is the same as those, same sign, too bright. But then the parameter sensitivity is different. But here, the N2 thresh parameter, this purple thing was dimming. Here, the purple is brightening. See, it's on the opposite side. So that's bizarre. That one parameter must be very strange. Let's look at these plots. Here's Siberia, here's N2 thresh. So recall how nice N2 thresh was for the Namibian region, which was this favored region. It's nice and linear. So here, it's looking like N2 thresh is behaving similarly. And then, oh no, it turns around, right? It's highly nonlinear, right? So this is the agony of tuning, right? So it actually, it doesn't have the same sensitivity that this region does. Okay, so that follows us there. Then there are some other regional biases which don't have to do with tuning trade-offs. So this one is a stubborn bias. We want to get back to the red line, but none of these simulations are close. There's just no sensitivity to any parameter. So we can sort of give up immediately there. This one's really interesting. So this is China. And what happens here is the default simulation is actually the best. And it's so nonlinear that no matter how you tune the parameters, it always gets worse. You're better off just staying at the default. So it really makes a mockery of this notion of sensitivity where it's like, well, it's sensitive, but so nonlinear. Okay, so what can we learn? We can learn a little bit about which biases are trade-offs and which are stubborn. And that's sort of a helpful first step. We kind of learn which parameters matter, and then we can look in those parts of the code to see, okay, this N2 thresh is a strange parameter, has strange behavior. Let's look there to try and make a model improvement. We learn when to give up. Like Jun basically spent 6 months at UWM hand tuning and we got nowhere. And so then we decided, okay, we need this tuner because otherwise it's too hard. If the tuner doesn't work, then we either need to find a new parameter or else we need to make a model structural change. So that's all I have. Okay, thank you.
Rich. Given you're doing all these 20-degree by 20-degree boxes, Bolivia was a good example. You're probably straddling competition between two parameterized processes, whereas in depth of the stratocumulus is just one thing. You think that plays a role in
Yeah, so what Jun has done is he's made some customized regions, which are more respect like the land boundaries and so on. So we've worked on that. One bizarre thing is we actually tuned originally with 30 degrees by 30 degrees. That actually gives a better answer. Like you get better optimal parameter values when you do 30 by 30. So it's a very strange sort of thing where, yeah, you'd think it'd be better to go smaller and smaller regions, but so far we're not finding that. I don't know.
But how do you deduce the physical and dynamical basis for this? There's a mathematical manipulation, but does it, how can you learn better physics and dynamics from this?
You can't. I mean, this is just going to give you some clues as to where to look, but this is like only the first step. You'd actually have to go to the equation, see where the parameters are embedded and how they're all behaving.
Oh, I see. You're not looking in nicely. Okay.
Have you thought about, maybe you answered the question, but when you said 30 by 30, you were talking about the model resolution, right? You were.
No.
Have you thought about trying coarser versions of the model to see if you get similar results?
Oh, you mean like a 2-degree version of CAM?
Yeah.
No, we haven't. We probably should.
And I also wanted to, if you have, maybe I'll ask you later, but the trade-offs between the Southern Storm Track and the Stratus X, that's something we always struggle with.
Ah, that's the slide I didn't show. Yeah, that leads to a very interesting one. I'll show you that later. Yeah, that's a weird tuning trade-off.
The question in this, I don't know who was first. Okay, Dave, go ahead.
Yeah, so first question is, do we have the capability here to do this with CAM? And what it would take? And so maybe that's something.
Yeah, we do. It's buggy right now. For some reason, it's not working. But Ben Stevens is working on it, and hopefully we can figure out whatever bug this is, and then yeah, we should be able to use it.
And then I'm also curious, related to the automated tuning that the GISP group is doing, which we're also trying to bring into the CAM framework. And they found this sort of thing where a lot of the parameters weren't showing a sensitivity until you got close to the right space. I wonder, it might be interesting to if that auto tuning ever works, retry the quad tune when everything's closer to right, and then see whether or not you're still having the same problems that you can't get there, because that's searching a bigger parameter space and a bigger set of targets.
It's
I don't know.
question. Like we are, it's simplified, so we're definitely omitting. It's definitely not a full-fledged tuning process like what GIS is doing. I just think about it. Yeah.
And Will?
We have time for that. So maybe I'm confused or on the framework or what the target is, but if you're only tuning club or this new club tau scheme, and then you have a comparison using the old club that is like with the tuning model, aren't you just tuning the new club to behave like the old club, or is this just like sort of a proof of concept of the?
Yeah. So so that's all it's going to do. It's going to tune new club to match old. So the philosophy is, okay, we make a structural change, and then that has some benefits. It matches the pattern better, but then somehow it throws the global mean way off, or there's some other. And so then we hope that if we tune the parameters, then we get the benefits of the improved structure, but also, recompensate those errors.
That goes back to Dave's questions. When the model is tuned maybe in closer space, you can rerun this process when you discover different sensitivities.
Yeah.
Okay, we gotta move on, sorry. But there's a club tutorial this afternoon. So next up is continuing with the theme of club. It's Kyle Nardi. You can sit or stand or do both.
I have a lot of clicking, something else to saying, but thank you. So for those of you I haven't met, so my name's Kyle. I just started as a postdoc here in CGD about a month ago, but what I'm going to present today is some of my work for my PhD at Penn State. And I was working in support of the Momentum Flux CPT, and I'm specifically interested in this talk in discussing the role of countergradient momentum fluxes in club and how it affects the general circulation in CAM6. So with the new prognostic momentum flux formulation in club, we can now account for countergradient fluxes, and we want to see how that affects the model general circulation. So since I'll talk about countergradient fluxes quite a bit, I'll just give a brief overview of what I'm talking about. So this is an example from Vince's 2019 paper. And countergradient momentum fluxes occur when momentum flux and vertical wind shear are of the same sign. And an example of that is shown here in the pink shading. And with the previous version of club that I'll call the diagnostic momentum flux formulation, we did not account for countergradient fluxes. So we related momentum flux to wind shear with this coefficient K, which was assumed to be positive. So now with prognostic momentum flux, we're able to account for countergradient fluxes and essentially situations where this value of K is negative. And a motivation for this work is that Colin, Vince, and I had a paper that just recently came out in James that looked at parameter sensitivities for certain club parameters. And we're mainly looking at the boundary layer, but what we found was in multi-decadal simulations, when we made perturbations to certain impactful club parameters, over long time periods, we actually saw quite a bit of influence in the general circulation, and those changes to what was happening in the general circulation was feeding back into the boundary layer and actually affecting some of our club parameter sensitivities. So we wanted to go in and see, well, if we think countergradient fluxes are going to change the degree of vertical mixing in the boundary layer, we want to see exactly how that vertical mixing is changing, and then how that change in vertical mixing is affecting the general circulation in these multi-decadal simulations. So to do this, we're going to run several 1-degree aquaplanet simulations. So we're going to run for 30 years. So I'm using this CAM development tag, and a lot of my previous work during my PhD was exploring the TAOS code that Vince mentioned earlier. For this these experiments, we're turning TAOS code off. So we have 4 different configurations. So first, I'm labeling PMFs. This is just the pure prognostic momentum flux formulation that includes counter gradient fluxes. And then we also have another configuration that we're calling PMF no CG, which is a configuration that's designed to resemble prognostic momentum flux, but we're removing the sources of the counter gradient fluxes, namely buoyant production and turbulent advection. And I'll describe exactly how we do that in a couple of slides. And then we also have a couple of diagnostic momentum flux formulations, so the old version of CLUB. The first we're calling high diff, so this is a configuration that's tuned to produce a relatively high vertical diffusivity. And we're doing that by tuning the CK10 parameter, as I'll describe in the next slide. And then also low diff, which is similar, but now we're tuning with a lower value of CK10 to produce lower vertical diffusivity. So these 4 configurations allow us to have several different ways that we can affect diffusivity in the boundary layer in CLUB. So these first 2 is doing so through prognostic momentum flux, and then these 2 here are through the old diagnostic momentum flux formulation. And we can compare and contrast how these 2 different methods of changing diffusivity affects the general circulation. So just as a review for the diagnostic momentum flux configurations, we are tuning this value CK10. So for the high diffusivity, we're using a value of 0.7, and then for the low diffusivity, it could be 0.3. And that's going to feed into this diffusivity coefficient, which then goes into the formulation or the diagnosis of momentum flux. Now, the prognostic momentum flux formulation, we're essentially using this equation here. That's a time tendency for momentum flux, and it importantly includes impacts from buoyant production and also turbulent advection. But then to fully understand the role of counter gradient fluxes. That. Oops. Oh, sorry.
Oops. So we're still sharing now, so you just need to go back.
All right. Thank you. So to fully understand the role of counter gradient fluxes, we need to include a configuration that resembles prognostic momentum flux but has the counter gradient fluxes removed, as I mentioned on the previous slide. So if we rearrange some of the terms from the prognostic momentum flux formula, we can get this diagnostic for momentum flux that includes essentially the old eddy diffusivity formulation, but also buoyant production and turbulent advection. And what we're going to do is remove these 2 terms here. So we're going to remove buoyant production and remove turbulent advection. And we're essentially going to get a diagnostic for momentum flux that looks like the old diagnostic momentum flux formulation, but we're calculating this diffusivity coefficient in a different way. We're using the eddy turnover timescale, C6, and also the vertical wind variance. So this is a way that we can essentially remove counter gradient fluxes, but remain within the prognostic momentum flux framework. And this is how we'll compare the 2. So first thing we do is we look and see how the momentum flux in a global integral sense is changing between these 2 experiments. So on the top here, this is when we're adding counter gradient fluxes, going from no counter gradient fluxes to prognostic momentum flux, and this is high diffusivity to low diffusivity, reducing CK10. And so what you see here at each latitude and longitude is a mass-weighted vertical integral of momentum flux. This is the magnitude of momentum flux. And then what you see in parentheses here, that is the global average of these vertical integrals. And the point we want to make here is that in both experiments, we're essentially getting the same change in globally integrated momentum flux. But what is differing between the configurations is exactly where the biggest decreases in integrated momentum flux are occurring. So with prognostic momentum flux, when we add counter gradient fluxes, we get more of a concentrated decrease in integrated momentum flux, whereas when we just decrease CK10, we're getting a more spatially uniform pattern. So there's a bit of a spatial variation in the change in momentum flux, depending on the method that we use. So we next ask exactly where these counter gradient fluxes are occurring. So this flux mask is essentially showing at each point the probability that you are going to get a counter gradient flux in the U direction and also in the V direction. So what's noteworthy here is that we have a high incidence of counter gradient fluxes in the subtropics, generally between 10 and 20 degrees. And then we also have a high incidence of counter gradient fluxes over the mid-latitude storm track. And now we go in and we look to see from a cross-section perspective how momentum flux, magnitude is changing, and then diffusivity. And what I'm doing here is I'm averaging over both hemispheres and looking from 0 to 40 degrees. And so first is momentum flux magnitude. So this is going from prognostic momentum flux with no counter gradient fluxes, then adding counter gradient fluxes, and then this is going from high diffusivity, the CK10 value, to a lower value, CK10. And what we want to note here is that momentum flux has a more prominent decrease around 20 degrees when adding counter gradient fluxes compared to when we just reduce CK10. So again, getting to the point that there is a bit of a spatial variability in the reduction in momentum flux when we add counter gradient fluxes versus just changing CK10. And then we can also look at effective eddy diffusivity, which I'm calculating using this formula here. So it's essentially momentum flux over wind shear, but this formulation of effective eddy diffusivity allows for negative values of K. So it allows for counter gradient fluxes to be depicted. And again, what we see is that there is a broad decrease in diffusivity in both cases. But reducing CK10 in the diagnostic momentum flux formulation seems to have a more uniform decrease in diffusivity. And probably hard to see here with the color bar, but there is a little bit of a difference when you look at prognostic momentum flux. There's a bit of a variation in the vertical, but also latitudinally. Again, making the argument here that in both cases we're reducing diffusivity, but in different ways, depending on if we're doing it through prognostic momentum flux, adding counter gradient fluxes, or changing CK10. I'll show there. So I also just wanted to show the spatial relationship between the change in effective eddy diffusivity and where counter gradient fluxes are occurring. So this plot is just a zoomed in version of this plot here. When we add counter gradient fluxes, what do we see with effective diffusivity? And what I have overlaid here is the combined frequency of counter gradient fluxes. So the lighter contours here imply that there's a higher incidence of counter gradient fluxes. And broadly speaking, we see some spatial relationship between the incidence of counter gradient fluxes and the highest reduction in diffusivity, implying that when we add buoyant production and turbulent advection, that is essentially countering potentially other terms that are producing momentum flux, for example, turbulent production. And so it seems to be some sort of influence here, some sort of relationship between the spatial pattern of diffusivity change and where the counter gradient fluxes are occurring. And so we can look at this also in a vertical profile perspective. And so first I show for different latitude bands, I do a spatial average over different latitude bands of effective eddy diffusivity. First for the high diffusivity and low diffusivity configurations. So this is just green is high CK10, red is low CK10. And we see this broad reduction in diffusivity, but the general shape of the diffusivity profile is retained. But if we go to the situation where we're adding counter gradient flux and going to prognostic momentum flux, we do get this decrease in diffusivity, but the shape of the profile appears to change a bit. I think of it as if you're pressing with your finger the green profile downward, but then you're not really changing anything below that. So below about 950 hectopascals, the first couple model levels near the surface, you're not really changing diffusivity, but aloft you are. So there's a bit of a change in the shape, and this provides further evidence that when we add counter gradient fluxes, it is reducing diffusivity, but it's doing so in a different way from changing CK10 as in the past. And I overlay everything here, and I also add this blue curve, which is the counter gradient flux fraction. So these higher values here imply that we have more counter gradient fluxes. And we generally see around 850 hectopascals, we have the higher incidence of counter gradient fluxes. And for the thicker lines where we're looking at the prognostic momentum flux, that's where we're getting the biggest changes, where the counter gradient fluxes are occurring. And so now I wanted to talk a little bit about how this is affecting the general circulation, and we're looking at this through the Hadley cell. So this is a situation where we're changing prognostic momentum flux, we're adding countergradient fluxes, and again, this is reducing CK10. And then this is the change in omega. And one thing that's noteworthy here is that in both cases, when we reduce diffusivity, there's an enhancement in the vertical velocities in the tropics. We're getting deeper blues here, we're getting higher values of these upward vertical velocities. But adding countergradient fluxes seems to produce a higher magnitude response in upward velocity near the equator. So I showed in a previous slide that in both situations, we're basically doing the same thing to the global integral of momentum flux. But in this case, we seem to be having just a bigger influence when we are adding countergradient fluxes on at least this aspect of the general circulation. And then we see something very similar in meridional wind. So with adding countergradient fluxes, it produces stronger equatorward low-level flow compared to when we reduce CK10. So as we saw with diffusivity, there was generally the same response in both experiments, but there was a different way that adding countergradient fluxes was changing diffusivity. It's the same thing here. We're getting the same response in the general circulation, but adding countergradient fluxes seems to be doing something a bit different. It seems to be producing a stronger response in that situation. And so lastly, I'll show a histogram here of total precipitation rate. So here in the top panel, and these are just partitioned by the higher values precipitation rate, lower values precipitation rate. So the pinks here are prognostic momentum flux. So this is showing that we're having and this is averaged over the tropics, all grid points over the time period in the tropics. And what we're seeing is that in both cases, lower diffusivity is producing enhancements in the frequency of the highest precipitation totals. But the shift toward favoring high precipitation totals is more prominent when adding countergradient fluxes. And we feel that's consistent with the higher magnitude response we saw in the upward vertical velocities near the equator, and also the equatorward low-level flow that we were seeing. I'll just show my takeaways here. So essentially, we're finding that we can reduce diffusivity in CAM6 in two different ways through club. So with diagnostic momentum flux, we can reduce CK10. With prognostic momentum flux, we're essentially going from no countergradient fluxes to having countergradient fluxes. So in both cases, it's reducing diffusivity, but adding countergradient fluxes produces a more spatially dependent reduction in diffusivity that we think is related to the spatial location of where these countergradient fluxes are occurring, where buoyant production and turbulent advection are occurring. And we're seeing that reducing diffusivity appears to increase the strength of the Hadley cell in these aquaplanet configurations. And we see that adding countergradient fluxes versus just reducing CK10, it produces a higher magnitude response. We see that in several different fields, and they seem to be visually consistent with each other. So our next steps are to better understand why these spatially varying changes in diffusivity are occurring and how that's affecting the general circulation, why it's producing a stronger response. And also looking a little bit more about which club budget terms are most important. So I don't have a slide on this, but we've seen preliminary analysis of these terms. It seems that the buoyant production term seems to be driving a lot of these countergradient fluxes versus turbulent advection, but that's something we're still looking into. But I'll leave these up, and yeah, if there's time for questions.
Thank you.
The answer to this is quite simple. The countergradient flux is a very simple connection to shear. Down shear, tilted eddies, whether it's in vertical convection or baroclinic instability, that produces the superrotation. I mean, this is well known. It goes back 50, 60, 100 years back.
Great.
Yeah, Rich.
That's an interesting signal you get at those extreme presets, 4 orders of magnitude kind of higher. I'm wondering, given that the countergradient terms are pretty low in the troposphere, I'm wondering, have you looked at the nature of that precipitation? Is it directly due to the change, or is it some kind of stability impact on duplicate effect?
No, it's simple squall lines.
Well, in the model, probably not score lines.
Well, whatever the model thinks it looks slower
Yeah,
is.
yeah.
That's a good question. So I haven't looked specifically at like the nature of the precipitation, but that is another next step, and that's a really good thing to think about. So I appreciate that. William.
So those inflow, sorry, I'm saying inflow, what I mean is the equatorward flow at low levels, it seems somewhat analogous to what's happening in the TC simulation.
Yeah, that's a good point.
Yes, in
More
fact.
inflow with less diffusivity.
Yeah, in fact, the two examples you showed, the mid-latitude eddies, that's a well-known theory of paraclinic instability. The one we showed in the tropics, it's shear parallel convection lines, tilted line along the shear. It's physically obvious.
Okay, great. Thank you.
Alrighty, let's move on. Thanks, Kyle. Next up is Ben Stevens. He's gonna use his own laptop.
Okay. Hi. I'm going to be talking about some very preliminary results that we have recently obtained using a recent version of the updated CAM. I believe these come from the 034 tag, so not quite the latest and greatest, but recent. They're not fully digested results. They're quite new. And so I can kind of give you a sense of what's occurring in these quarter degree resolution experiments. They're 10-year experiments. The main two that we're going to be looking at is one with the old diagnostic momentum flux scheme in club, and then the new one has the new prognostic momentum flux scheme turned on. These are expensive simulations, so we haven't done any tuning really, but we're just kind of turning those momentum fluxes on and off. So I'll just talk about kind of what that's doing with respect to cyclones. It's standard practice, of course, to acknowledge your collaborators. I want to take that a step further, I think, and go ahead and actually give essentially full credit for this talk to some of my collaborators, especially Colin and Julio, who pretty much held my hand through this, because I work on club and turbulence, and cyclones are totally new to me, as well as these high resolution experiments. So, and Cecile, I want to thank for doing the actual experiments, and Kyle also for his comments on some of the results. Okay, so Kyle just gave a sense of what's changed in club in the new version of CAM. CAM 5 and CAM 6, which I'll show some results from those. They both used diagnostic or down gradient momentum fluxes. CAM 5 was a different turbulence scheme. CAM 6 did use club, but with diagnostic momentum fluxes, with K defined the way you see here. It's a turbulent length scale times the square root of the turbulence kinetic energy. The major goal of the Momentum CPT, the climate process team project that I've been funded under, has been to turn on these prognostic momentum flux, this code in club, and test it and tune it and see how it works. So almost all of my work has been in like 1 degree simulations, but this is how the equation looks now. It's a much more complicated equation, but more realistic in terms of its physics. Yeah, I think that's all I wanted to say here. Yeah, in the new version of CAM, you will be able to revert easily to the diagnostic momentum fluxes if you want to. It's just a nameless flag. Okay, so these are some results from Tempest Extremes. So thanks to Colin Zarzicki for his help getting that working. And then up top, I have some observational data from IB tracks. you know, someone more practiced than me or more knowledgeable than me could probably delve into this in more detail. But I think one feature that looks like it might be better in the prognostic case is the kind of northeastern part of the Atlantic relative to the diagnostic case. So this is just a brief look at what these storm tracks look like in these two 10-year simulations. Just wanted to give a sense of that. Colin looked into this in a little bit more detail once the runs were completed. And I wanted to give a little summary of some of the things that he pointed out. So for example, we actually beat CAM5 in some ways with our new code, whether we're using diagnostic or prognostic momentum fluxes. So the accumulated cyclone energy looks better than CAM5 in some ways. The high Central Pacific bias looks like it's improved from CAM5, with again prognostic momentum flux being a little better than diagnostic. And then things like the average duration of tropical cyclones, the maximum intensity, the newer code is doing better than CAM5. So those are pretty positive results, because as I understand it, CAM5 was relatively skillful with respect to TCs. Some of the challenges that Colin pointed out, we're producing too many tropical cyclones. I can't remember if he said that this was also a problem in CAM5 or not, but I feel like he might have said that. It's about 2 times what we see in observations. So that's one bias. And Colin pointed out some concern that this seems to be occurring even with the updated microphysics, and had previously found in a paper that MG2 was an improvement over MG1. But one idea is that if we could bring down that cyclone count, maybe through tuning of ZM, for example, without affecting these other patterns, then Colin's opinion was that this updated version of CAM would actually be a pretty good model, one of the better ones at quarter degree resolution. So with respect to inflow angle and depth, another metric I've only recently learned about, it looks like prognostic momentum fluxes are doing quite a bit better than diagnostic momentum fluxes. As I understand it, the observational value for the inflow angle, which I guess as I understand it is sort of the deviation from geostrophy as the wind is turning around the storm. Observationally, I think Colin said it should be around 20 or maybe 22 degrees or so. We're not getting that quite right, but certainly prognostic looks better than diagnostic, both in the Northwest Pacific Basin and in the North Atlantic Basin. And we're showing the appropriate kind of anti-correlated relationship between the inflow angle and the inflow depth. So that's nice to see. These are composite storm plots. These are, I think in the North Atlantic, there were somewhere in the area of maybe 500, give or take, storms in the diagnostic and prognostic cases. And these are basically averaging over storms in that region that have central pressures or surface pressures less than 97,000 pascals. One of the kind of nice things about the prognostic momentum flux run is that the sort of maximum winds are a little bit more, they're a little bit more focused, kind of, and lower down, they're a little more concentrated. This kind of goes along with some of what Kyle was saying about the new prognostic momentum flux code being less diffusive. The maximum winds seem to be spread out over a larger region here, and we're getting a stronger and inward contraction of the inflow here at the surface. So these are composites for the North Atlantic. This is the same kind of plot, but it's for the Northwest Pacific, and I believe we see some of the same kinds of improvements. I mean, the winds do appear to be stronger in the diagnostic case, but the strongest winds seem to be a little closer to the ground. I think in the prognostic case, but I think in either case, ideally the strongest winds would be closer to the ground, like maybe under 1,000 meters. Maybe still room for improvement. But again, we haven't done any tuning or anything like that. This is just flipping on the switch and seeing what it looks like. I thought I would end with this plot from Colin, which is a nice plot. It actually incorporates observations, Cam 5, Cam 6, and the updated version of Cam with both diagnostic and prognostic momentum fluxes. So this is the pressure-wind relationship. And yeah, as you can see, Cam 5 was, at least in this respect, relatively skillful. Cam 6 was a bit of a degradation. The improvement that we're seeing in the updated version of Cam, I don't know what to attribute that to. I'm sure there's been, there's obviously been many structural model changes, parameter changes, since this this Cam 6 baseline here. So I don't,
Can you clarify the colors? I can't see.
Oh, I'm sorry about that. Yeah, let me clarify that. So the blue is the OBS. That's the top line. Red is Cam 5. So Cam 5 and OBS are fairly close together. Cam 5 was sort of skillful in this respect. Cam 6 is the one that's at the bottom. That's the one that where this relationship seems to have degraded. Our updated version of Cam is doing better. We're not at Cam 5 level yet, at least in this regard. But the orange line is the prognostic momentum flux, and the purple line is the diagnostic. So here again, we are seeing a little bit of an improvement from prognostic, from using the prognostic momentum flux equation. But again, can't attribute. I would not know exactly how to account for all of the improvement that we're seeing here versus Cam 6 in the updated version of Cam. But yeah, thanks again to Colin for this particular plot. And I think that's all I wanted to show you currently. As I said, we're sort of literally just digging into these runs that were just completed weeks ago. And so there's a lot to learn, but I think the intention is that we'll write something up on this as a nice result from the CPT. So just summarizing some of those points, we've turned on the prognostic momentum flux code in the CPT. There are some improvements over Cam 5 in some ways. Overproduction of TCs is something that is still a bias, I think, but could potentially be mitigated, maybe with some ZM parameters. Yeah, some of these other points that I was just making about how prognostic momentum flux seems to look better than diagnostic momentum flux. So yeah, thank you for listening, and I'm happy to listen to your questions. And if you're lucky, there might be somebody here who can answer them.
Just a quick clarification. When you say Cam 6, it has 32 vertical levels, and the Cam 7 has.
I believe that's right. Yeah, that's right. Yeah.
Adam?
So maybe Cecile can clarify, but didn't you do some Cam 7 quarter degree simulations with Cam 6 vertical levels?
Yes, we did. Yeah, we did, but not with your prognostic. But we did some. We tested the vertical level, the 93, the 58, and the 32.
Was that in this latest round of runs that you did maybe in December or so?
Yeah, it's on the page. Yeah.
Might be interesting to look at those results then. And see.
Yeah.
You haven't looked at that. Thanks for pointing that out.
Sorry. No. I think if we can figure out how to tune club to the prognostic momentum flux to make if you sit a little shallower, the inflow angle will.
I think we could boost it.
Right up.
Yeah.
Could you tune that with individual storms? They don't have to run 10 years?
Probably.
Rich?
In terms of cycle times, I've always wondered that, should we expect 25 kilometers to be correct? There is, I mean, there may be a thinking that Cam 6 is actually correct, because if you went to like 10 kilometers, you'd be closer to the target. Whereas, this is unanswerable, I guess, but like, whereas, you know, Cam 5, maybe if you go to 12 kilometers overshoots and you get these super intense hurricanes.
Yes.
Which my minimal experience of some old, very old, 12 kilometer ones, you see some pretty darn intense systems. So it may not be so bad, but all these simulations are underperforming, doing that relationship to increase it.
Yes.
Anyway, sorry.
To your knowledge, Julio, are those all 25-kilometer simulations, the Cam 5 and Cam 6 that Colin was using? Do you-
Yes, they're all 25 kilometer simulations, and the problem has always been to get intense enough winds. I mean, and then there's all these weird scalings people apply to, you know, in basically invent a 10-meter wind speed from the model's lowest level wind speed. So there's a lot of things like the pressure wind diagnostic. I think you have to look at it carefully, because there are a lot of assumptions that go into the wind speed. Not assumptions, a lot of massaging can happen.
Okay, thank you, Ben.
No problem. Thank you.
So next up is Adam Harrington. You're gonna present yourself?
Yeah, I'm gonna try to steal the screen and just use my computer.
Okay.
It looks like I was able to do it. Hello, everyone. I'm Adam. Sorry, I'm getting over a cold. I thought it would have been gone by now, but unfortunately it's hanging on. So I sound a little hoarse. But we'll try to get through this without passing out. I want to provide updates on the Unified Turbulence and Convective Parameterization Club MF that I've been working on for several years. The PI of this project is Jawczek Share over at JPL. The co-PI at NCAR is Julio Beckmeister. So just to set the stage, we're developing a parameterization using the eddy diffusivity mass flux approach. And briefly what that is you are parameterizing your turbulent fluxes, W prime, psi prime bar, as having an eddy diffusivity component, followed by a mass flux component. And the eddy diffusivity component is going to represent mixing by small scale turbulence. It's parameterized using down gradient diffusion. And then the mass flux term is going to represent asymmetric mixing due to convective plumes. So we model the mass fluxes with a plume model. We initialize the mass fluxes by constructing a PDF near the surface of thermodynamic and vertical velocities, then sample from that PDF at the surface to come up with an explicit ensemble of plumes. And each one of these plumes is using a stochastic lateral entrainment rate, which is given by this formula here for the fractional entrainment. Effectively, this squiggly P here is a Poisson distribution. And so the stochasticity comes from randomly sampling from the Poisson distribution. And that Poisson distribution has a mean, which is inversely proportional to what's called the entrainment length scale. And that's the vertical distance that a parcel would travel before experiencing one entrainment event. So basically this squiggly P thing is going to return the number of entrainment events that occur over some distance delta Z. So for Club MF, what we did is, what we envisioned is sort of replacing the down gradient diffusion eddy diffusivity component with Club's high order turbulence model in order to represent the small scale turbulence. And so effectively what we're doing from that sense is we're augmenting Club with plumes. That's effectively what this project is doing. So I wanted to go over sort of the history, the version history of ClubMF. So we first started off doing having the mass fluxes do shallow convection by just using a fixed entrainment length scale. In that first version, we were able to demonstrate the usefulness of ClubMF, and that's shown here. This is a grid box in the Bomix case, single column model case. And it shows the subgrid distribution of theta L, which is liquid water potential temperature, and total water in the y-axis. And the club will produce a joint PDF in this particular situation that looks like these black lines here. The LES solution, which is our target, has a much more broader distribution that is skewed towards the upper left-hand side of the plot. And so then the discrete mass flux plumes end up populating this side of the space in order to add sort of this missing skewness from the club PDF. And so this demonstrated the utility of this approach. We then moved on to a more general version called club shallow plus deep. And the way that we make these mass flux plumes do both shallow and deep is that entrainment length scale is now dynamic. And we simply just set it as some complicated function of the environmental relative humidity, which works. But it's just kind of more of a relationship. It's, you know, the cause and effect type. Does convection create relative humidity, or does relative humidity create convection? We're sort of just doing away with that. So it's sort of a lowered approximation, in my opinion, for the entrainment rate, but it kind of does the right thing if you want to compute, have your scheme do shallow and deep convection. And just to give an idea of what that looks like in a single column model case, this is the LBA single column model case over the first 10 hours here. And I'm just showing the top of the plume ensemble. And so in LES is the dashed line, you have sort of this gradual growth of the convective plumes throughout the day. The shallow deep is these gray lines that have these sort of high frequency oscillations. And then the dark, thick gray line here is CAM 7, so the ZM scheme. And so it doesn't have this nice gradual growth of convection like you see in LES and observations. You kind of have this on-off behavior of ZM. I'm sorry, you have this on-off behavior of our first iteration of ClubMF that kind of matches what ZM's doing. The latest version that I've been putting together is called ClubMF Aero, and it has lots of enhancements over this previous version of ClubMF. I've just developed a dynamic entrainment length scale calculation that's primarily a function of the plume's history, mainly the plume height at previous time steps. We've included downdrafts, explicit downdraft ensemble to provide some downdraft physics such as rain evaporation. And that allows us to, well, I should say rain evaporation is what drives downdrafts. Getting that right produces your negative buoyancy that creates the momentum for these downdrafts. And that gave us the ability to utilize a cold pool feedback, which is informed by the strength of the downdrafts. And effectively, the larger the cold pool feedback, the more it increases the entrainment length scale. That is, the larger distance a parcel has to travel before it experiences an entrainment event. So these three pieces here yield this red curve in the LBA case. It gives us a more gradual growth of the convection throughout the day. And that's a result of both the plume history and the cold pool feedback. Other important aspects of ClubMF Aero are, as the arrow implies, we have coupled the MF plumes to cloud aerosol interactions so that you can now nucleate and activate cloud and ice droplets using the updraft velocity from the mass flux plumes. Passive tracer transport is just something that is important to have for the general circulation and getting your constituents correct. And then we've also done a convective initiation, a loft trigger. That is, we've generalized it so that we don't just construct a PDF at the surface to initialize the plumes, but at any arbitrary vertical level, we've constructed a PDF where you can initialize the plumes. I just want to say that one of the targets of this project is to provide something that's competitive with CAM7. And CAM7 has obviously been developing over the last few years. And so one of the technical challenges is constantly merging up our Club MF branch to be current with the head of the CAM trunk. And that's actually a lot easier said than done. But it does allow us to do comparisons with the latest and greatest CAM7. So for the rest of this presentation, I'm just going to be doing an evaluation of some aspects of Club MF Aero against how it might be different from CAM7's latest and greatest. And we've done this using AMIP runs, 20-year AMIP runs from 1998 to 2017. So the starting point is the view basically I like to take from 35,000 feet, or at least that's the approach I'm taking here, where I'm constructing a Taylor diagram that shows the skills of various variables, the global skill of various variables, which I've listed here. And so each one of these variables, I have a corresponding observational product, and series is on here a lot. So I was very interested in Jonah's talk about better model observation comparisons. But I also appreciate even putting together this library of observations that a lot of it's from Brian Medeiros, but having that sort of script workflow is a lot of work in itself and took a lot of while to put this together. So it's not perfect, but I think it's pretty decent comparison. So the Taylor diagram, most of the fields we're looking at look very similar to CAM7, and so they get the OK button. For example, all of these fields in here are very close to the reference or observational spatial standard deviation. That's this dotted line here. They have high pattern correlation coefficients. That's this numeric value here. And the distance, I guess I should say the distance from this reference point measures your centered RMSE, and they're all close. So all these things are lumped together, and these are kind of your ERA5, T850, QE50, PSL. So you can more or less kind of say those are fine. Things that stuck out are related to clouds. So long wave cloud forcing is number 3 here. So in CAM, we're sort of doing pretty well. And then I jump up here into Club MF with a higher RMSE and a much larger pattern standard deviation. That's also seen in liquid water path compared to ERA5, which is here 6. So we kind of go away again from a more reasonable pattern standard deviation to a much larger pattern standard deviation in RMSE. So those are 2 that are degraded, but there is one that's significantly improved at this view, and that's the ice water path. And so CAM7's ice water path relative to ERA5 has pretty poor, weak, I'd say, pattern standard deviation, and we've improved it significantly going to Club MF. And so I'm going to sort of zone in on these liquid water path and ice water path and related cloud radiation variables. So these are the 2 simulations in blue and red again, CAM7 Club MF Aero. I have an intermediate one, Club MF version, which is that older version of Club MF. And then I also included CAM6 on here. And I'm just looking at, in this first case, liquid water path in the zonal space. I'm using ERA5 and then this remote sensing product called MAC-LWP, which is masked out over regions where there's a lot of precipitation and the product doesn't return a very accurate result. And so you'll see there's masked out regions in this zonal plot. But the black lines are the observations, and sort of in these these subtropical to tropical regions, they generally have more liquid water path than the blue line, which is Camp 7, and the gray line, which is Camp 6. And then our Club MF versions in the gold and the red have a little more liquid water path in these subtropical regions, more closer to the reanalysis. At high latitudes, in all model cases, we tend to produce too much liquid water path, especially over the Southern Ocean. Going from Cam 6 in gray to Cam 7 in blue always has this impact where it reduces your liquid water path. It also does this for ice water path. This is a consequence of going from MG2 to Pumas. For ice water path, you're sort of even more desolate when it comes to observations. A lot of the remote sensing products, as shown in this paper, sort of combining a lot of them and pointed to me, Brian Medeiros, is they really don't agree on magnitude of ice water path. They also pointed out that most of the ice water path products include condensates like snow and hail. And the product I'm looking at, the variable I'm looking at is literally just cloud ice water. So it turns out only ERA5 and MERA provide that restricted definition of ice water path. And so those are the ones that I'm just going to compare to because that's all there is really. So in the upper right is the ice water path. And Cam 7 in the blue noticeably has less ice water path than the reanalysis in the black. And one thing I added here is in the thin blue lines are a little perturbed parameter ensemble we did over the last couple of weeks to try to boost cloud ice in Camp 7. So we pushed all the knobs that we knew that increased cloud ice as far as we could reasonably push them without being completely indefensible. And so this just sort of shows that we can get some cloud ice water paths that are higher over the Southern Ocean compared to reanalysis, and over the equator and hemisphere. So we can push those knobs and we can help in certain regions, but there's a limit to how much ice water path we can generate through increasing these Cam 7 knobs. And so in Club MF, you'll notice, Club MF Aero at least, you have all of this ice water path over the Southern Ocean, and you have a lot more ice water path over the equator and over the Northern Hemisphere. And so that's really showing that, you know, our Club MF is doing something that you can't, we're creating more cloud ice than you could create by just tuning Cam 7. So there's some value to be added there. And a lot of this has to do with coupling the mass flux updraft velocities with the ice nucleation rates. And so this is the ice droplet number below here, and obviously you can see Club MF Aero produces a lot more ice number at the equator, and even over the Southern Ocean, which is partly responsible, or not mostly responsible, for the increase in ice water path. In Club MF Aero, that is more similar to the reanalysis magnitudes. So taking a deeper look at the cloud water, we can look in the vertical here. And so the top row is L58 Cam 7 versus ERA5, and Club MF Aero versus ERA5. And you can see the sort of dry bias relative to ERA5 and the cloud liquid that's over a lot of the subtropics and the tropics, that once we go to Club MF Aero, it moistens things up and the biases aren't as bad. But it does over moisten things up in the high latitude regions. This is shown here in a map plot, showing the same thing of the liquid water path for Cam 7 minus OBS. So we have sort of all this red or dry reduction in cloud liquid relative to OBS in the subtropics. And then if you go to Club MF Aero, you sort of moisten up those regions quite a bit more, but you kind of moisten up everywhere. So now your sort of Southern Ocean regions have a little more too much ice water path compared to observations. And these all sort of map onto the cloud radiative forcing. So the shortwave cloud radiative forcing is given in the second row. And you can see in Camp 7, we have these sort of red spots or sort of, you know, the cloud liquid over the marine stratocumulus regions, over the DICOMS regions, and the Vogels regions were too little compared to Ceres. And so when we go to Club MF, we've sort of helped a little bit with the cloud radiative forcing over the DICOMS region, and then to a lesser extent over the Vogels region. So I'm going to do the same thing for cloud ice, which is just in the lower panel. So the ERA 5 has a lot of cloud ice, and so when you compare it to Camp 7, you get all these negative biases aloft. And when we go to Club MF Aero, basically you just reduce those by some amount. And in the case of the equator, you actually start to, looks like you're forming ice clouds higher than what you even see in ERA 5, which is a property of Club MF. We have deeper convection, which I'll show in the next slide. In the horizontal, the ice water path biases, you can see for Camp 7 here there's a lot of blues, but there's also some neutral values that aren't so bad. And if you go to Club MF, now we're starting to get a lot more yellows, meaning we have more ice water path than in observations. But we're definitely getting a lot more ice water path at mid latitudes compared to Camp 7, which is notable and consistent with the last slide. And then the more ice water path you have, the more long wave cloud radiative forcing you have, and so you tend to have similar your long wave cloud radiative forcing bias plot looks similar to the ice water path bias plots. And again, you see we just have all this long wave cloud radiative forcing in the West Pacific, and that's related to Club MF just producing so much cloud ice at very high altitudes where the temperatures are cold and the clouds can't radiate long wave out to spaces effectively. So I'm just going to end on this plot that I've shown before that just looks a little more granular at the vertical profiles of Club MF versus Camp 7 in the West Pacific region. And so blue and gray are Camp 7, and all the other colors are some flavor of Club MF. And this one, first upper left plot is your potential temperature bias. And as I've shown at previous workshops, Club MF tends to produce a warmer tropical atmosphere, and it also tends to be moister. So in the region between 6 and 9 kilometers, you have a deficit of moisture in Camp 7 compared to ERA 5 that is more similar to ERA 5 in all the Club MF iterations. And so, but I want to highlight that, it's not just we're activating more clouds because we're hooked up to the aerosols. One of the reasons we have a lot of cloud ice at higher altitudes in the tropics is because this is the convection tendency of moisture. And so I'm highlighting where Club MF is detrainment layers primarily in this 9 to 14 kilometer region. And so it's detraining at very high altitudes, which is quite different from ZM, which ZM stubbornly seems to always detrain at about 500 hectopascals. That's kind of its main detrainment layer. And so that's something that's very qualitatively different in Club MF than ZM. And so that's primarily the main difference between Club MF and ZM. Their actual mass fluxes, the magnitudes of them are similar, and so it's and those are given in the lower left. And then I haven't shown any tropical variability. I have at previous workshops in that the variability is quite similar to what you see in Camp 7. I've only evaluated them in AMIP, and there's also, the tropical variability in AMIP is sometimes, at least when it comes to the MJO, not as good as in coupled simulations. So saying that our tropical variability is competitive with Camp 7 and AMIP, only goes so far as to Camp 7's AMIP isn't necessarily the gold standard for tropical variability. Okay, so that's sort of what I've learned about Club MF and how it's different than Camp 7, and so from there I'll just take any questions you have.
I have a different interpretation about what's wrong with convection in both models, coupled and not. In the tropics particularly I'm talking about, there is definitely a deficit of the amount of deep convection in the tropics. And that there's a very good reason for this. In the tropics, the sensible heating and the latent heating produce a very interesting mean state thermodynamically. I won't go into details here, but it's completely consistent with the absence of deep overturning. And I'll talk to you about this in detail, not right here. But I had a similar problem at the SMWF model many years ago. And it was running schemes that were not doing enough vertical mixing. When we put vertical mixing in, it made a huge difference to the mean state and to the precipitation. And so I have a paper on this. You may want to look at it, but it's very consistent with what's going on in CAM and CESM. And it's actually quite easy to fix.
All right, question from?
So the longer forcing got worse, but the ice, how liquid ice got better. And do you think those are related to each other?
Yeah, I think they're related to each other. Yeah, that's the sort of paradox that we're sort of dealing with here.
Yeah. So do you think, like, what are your thoughts on what would be causing it? Do you think it has to do with the liquidated optics of the ice clouds, or is it something that's kind of being exposed by the changes in the cloud liquid ice or the clouds?
Yeah, I mean, I could only guess at this stage, and you know, we could be producing a sensible amount of ice water path, but our TMGPs, you know, emissivity associated with that ice water path, that transfer function may be problematic. I mean, I don't know, but you could get, that's one reason why you could get the water right and the radiation wrong. Or it's the other way around. Maybe the radiation is taking a bad ice water path, or maybe the actual transfer function is accurate, and that the ice water path observational data set I'm using, which again is ERA5. I mean, I'm kind of I think we're kind of flying blind to some extent when it comes to the comparing ice water observations. So I'm not really at liberty to say whether Sirius is wrong or ice water path is wrong, but it seems like one of them has to be wrong. Or not Sirius, or I should say our TMGP's transfer function, or whether the observations are deficient on one end. It's just, I don't know the answer to that.
Okay, we gotta move on. Thanks for giving your presentations. Next up is Chenchen Liu from CU Boulder.
Hi everyone, I'm Chenchen Liu from CU Boulder. I work for Brand Toon. I'm also a visitor at NCAR ACOM, which we did is Simon. We work closely on CSM Karma model. Here we are going to talk about a sectional cloud microphysics model in the CSM2, and thanks for our co-authors who help develop and evaluating this model. The background picture is taken from the Pikes Peak in Colorado Springs last summer. So it looks like the clouds are in the mid latitude around 5 kilometers like that. Clouds are critical to climate system, but remain highly uncertain in climate models. The current cloud model in the CSM2 here after MG separates cloud-sized particles from rain source and snow. It uses Planck microphysics, while Karma cloud unites the different sizes from liquid cloud-sized particles with rain and ice grapple cloud-sized particles with snow. We use single size distributions and uses beam microphysics. So like the figures here, like MG uses Planck microphysics, which assumes the size distributions, while our Karma cloud use beam microphysics, which resolve the sizes in each beams. Here is a schematic diagram for CSM2 Karma Cloud. We have 3 categories, like we have Karma Cloud, we have ice, we also added graphos in these versions. We have 48 bins spanning from 0.3 to more than 4,000 microns for liquid cloud, and we have 48 bins for the same bins for ice cloud, but we have large particles in the largest bins, which is about 10 times of liquid cloud, so that we can include the large particles for snow. Those microphysics colored in black represent what we already have in the Karma, and those processes in green is our future development. Like the black colors, we have growth and correlations for each categories of Karma Cloud. And for those colored in green is our future development plan. Like we have immersion freezing. We don't have immersion freezing right now, and we plan to add ice multiplications to fix the issues for ice cloud. Back to the history of Karma Cloud, we have Chuck Bodins in 2013 had developed the Karma series cloud, especially for the improvement for tropical series. And we have Chris Molonia in 2022 who developed the interactive aerosols like dust and surface to interact with ice clouds. And here we developed and evaluated the Karma liquid cloud, and we combined with the previous ice cloud, and we also added the graphos. So right now we have implemented the Karma cloud into the CSM2. Hopefully we want to release this code this year.
Hey, I think folks online are saying that they're not seeing this. They're seeing, I think Adam, you might still be sharing it.
Yeah, I'm seeing it.
I'm seeing
it.
I'm seeing it too.
They're saying we see.
I can sign out.
All right, maybe it's just this person.
Yeah, it's working on my computer.
Because I took over, so.
Okay. Yeah. Okay, he said that worked. So he was like, okay.
For the cloud operation is computed by the CAM6 club. Karma either MG or Karma Cloud didn't do the cloud operation, but we use the input from club. Those differences between MG and Karma Cloud means there might be some feedback into the club. So we also need to adjust the microphysics. Hopefully the club tutorial this afternoon will be also helpful for us. So those figures, we have MG, Karma, and the data from left panel, mid panel to the right. And for the x-axis, we have latitude, and the y-axis represent altitude from 0 to 18 kilometers. So for both of these models, we have biases low compared to the data in the boundary layers, like within 0 to 2 kilometers. And for Karma Cloud, we have biases low in some regions like 60 north and 60 south in the altitude of 2 to 6 kilometers. And for MG, there are some biases, which bias is high compared to the data in the regions, in the circles, like in the mid altitude and in some like 4 to 10 kilometers in the middle altitude, and in the tropics, in the open atmosphere. But we want to note that this cloud operation can be tuned by the club. So that's what's the next step we want to improve. Karma Cloud captured the patterns for liquid water parts, but has large values like 30% to 50% more liquid water parts than the data. Here we define the cloud water parts, on the top row, which means the cloud-sized particles for liquid water parts, and we also defined the total liquid water parts, which means the cloud-sized particles plus the raindrops in the atmosphere before it falls onto the ground to form precipitations. So we have mg on the left, camera in the middle, and the data on the right. So it looks like for the patterns of cloud liquid water parts in the tropics, Karma Cloud has captured these patterns, but has large values, while MG has lower values. And for another patterns from East Asia to Middle Pacific, so it looks like Karma has captured these patterns well, but has large values, while MG doesn't have these patterns. Instead, MG looks like has a pattern in the North Pacific, which is not seen by the data. Overall, for the South Ocean, we have similar findings like Adam just said. We have biases high in the South Oceans with much liquid water parts, and it remains a problem in our Karma Cloud. So overall, the average mean global average mean values of cloud liquid water parts is about 30% more than the data. For the total liquid water parts, we have similar patterns, but look at the average mean values, we have 40% more than the data. Karma Cloud also captured the patterns for liquid water parts ratio. The ratio is defined as the ratio of cloud to total liquid water parts, which means how many liquid water parts contains the cloud-sized particles. So here in this figure, we plot the patterns for liquid water parts ratio greater than 0.5, which means more than half of these liquid water parts are cloud-sized particles. And those red colors means the ratio is greater than 0.85 or 0.9, which means the liquid cloud-sized particles dominate liquid water parts. So we have similar, for Karma Cloud, we have similar patterns than the data, while the values is about 0.66, which is smaller than the data, while the patterns looks good. But we notice that this ratio is sensitive to the size cutoff in the Karma Cloud. Like in the panel B, we have cut off the sizes into 30 microns, while in panel D, we have cut the sizes into 50 for cloud-sized particles. Now the values looks larger than the previous one and is now greater than the data. So it's for the MG, we looks like it lacks of some areas in the circle areas compared to the data. But for Karma, we have a good pattern. Karma Cloud is close to the observed effective radius of liquid cloud. For the figures below, we have probability density functions of effective radius over the oceans on the left and over the land on the right. So the horizontal axis represents effective radius from 0 to 30 microns for cloud-sized particles, and the y-axis represents the PDF distribution. Karma is colored in blue, MG in green, and the data in orange. So for the oceans, we have the peak effective radius of around 14 microns, which is consistent between Karma Cloud and the data. And for the effective radius of the land, it's about 12 microns. And so the differences between ocean and land represent aerosol cloud interactions because there are more aerosols over anthropogenic aerosols over the land and more CC, and therefore the sizes of cloud particles has decreased due to aerosol cloud interactions. Karma Cloud has captured these patterns very well and is produce reasonable aerosol cloud interactions. For MG, the peak effective radius looks smaller than the data with about 10 microns over the ocean and 9 microns over the land. Cloud radiative forcing and albedo is very important for climate models, especially if we like to do some climate projections in different scenarios. Here we compare the cloud forcing to the data. We find simulated shortwave cloud forcing is comparable to data. Spices is within 5% on global average, while simulated long-wave cloud forcing is about 50% lower than the data. So those figures shows shortwave cloud forcing, long-wave cloud forcing, and total cloud forcing from left to right. And the horizontal axis shows the values for each variable, and the y-axis is the latitude. So like for the shortwave cloud forcing, on average, we have good patterns for both of these models, while we have some high values in the tropics and in the South Oceans. So like in South Oceans is probably due to large liquid water pairs, and in the tropics might be in Karma is probably due to the still due to the large liquid water pairs, and MG probably due to the smaller effective radius. And for the long wave cloud forcing, it has larger biases compared to data, which is around 40% lower than the data. This is mainly due to the we have lack of enough high clouds in the model. Like the high cloud is not high enough, or we don't have enough ice water paths or ice water content. And similarly for the total cloud forcing, which is mainly due to the biases in the long wave cloud forcing. Simulated albedo is comparable to the data. So here's the figure for the time series of albedo for Karma, MG, and the data. So we have pretty similar albedo, annual mean albedos in these figures, which is around 0.29 for all these data and the models, and the relative errors is smaller than 1%. To conclude, we have a global climate models with sectional cloud microphysics, and Karma Cloud has captured the pattern for liquid water paths, but has a large values. We also have for the effective radius, which Karma Cloud is close to the data, revealing reasonable simulations of aerosol cloud interactions. Both of the MG and Karma Cloud has good patterns for shortwave cloud forcing and albedo, while the longwave cloud forcing has some biases. So here's some of the future improvements. Like we want to adjust the macrophysics for cloud fractions. And right now we don't have interactive aerosols for liquid clouds. For those biases for the ice cloud, we plan to like add the ice multiplications and add immersion freezings. And lastly, we want to improve the computational efficiency without sacrificing much microphysics. Thank you.
Thanks. Questions or gentlemen? How much more expensive is Karma roughly compared to MG?
Right now in current version, which it is about 10 to 15 times of MG, which is pretty expensive.
Do you also advect, do you need more traces advected as well?
Yeah, we do have more traces. Yeah, okay. And we have 48 beams, so that decreased the speed.
Yeah, okay.
So for cloud liquid and cloud ice, you have 48 different tracers for each one of those.
We have 48 bins, but the traces is also we also have more traces.
Oh, yeah, I'm counting a bin as a tracer.
Yeah, kind of.
Right. That concludes our series of AMWG talks. This afternoon, Ben Stevens is going to run a club tutorial. Online folks, if you haven't done so, if you want to attend, you need to register to get the link. So, thanks everyone.
Have you experimented with micro MG DCS?
Micro MG
DCS?
Oh no, I didn't.
I found that increasing that does increase the cloud fractions at those high latitude, mid altitude regions that you're looking at. If you just, right now it's at 500 microns. I'll try setting it to 600, and that'll make the ice cloud lifetime last longer.
Yeah, that's why I want to ask you about the cloud fraction. Have you looked at?
I
Can you move
don't know.
the thing before somebody
I just know that the only way I could increase